Hello. I should say good evening, good afternoon, and good morning. And I think that's the right order because we're starting with our friends in the Asia Pacific region. And today we have a truly global event that's going to happen over the next 3.5 hours. My name is Sean Waltman. I am Google's cloud geographer, and I'm super excited to be hosting this event today. I hope that you all enjoyed day one of the conference and the many keynotes and new feature launches and lightning talks that we have. And we have some amazing talks in store for you all today. And I want to thank all the participants here for many things. First of all, for the whole idea of this event, this specific meetup at Geo for Good came from user feedback, came from your feedback over the last 2 Google Earth Engine and Geo for Everyone, Geo for Good events. We heard loud and clear that practitioners in the public sector who have unique challenges wanted to be able to make more connections with Google Earth Engine users that are in similar positions. And we also wanted to highlight some of the work being done in higher education, especially work that is pertinent to public sector agencies and the policies and products that their work ultimately influences. So when we started planning for this public sector track, I had a very, very different in-person event in mind. And of course, all of that changed. As Rebecca, Hema, Nithya, and Raleigh touched on yesterday, everything going haywire in your world, having to care for loved ones and change your daily routine. The fact that you still made time across all of these time zones to be here and share your work on the global with your global colleagues means a lot to me, and so I really appreciate that. And while it seems that the entire world has been focused on the goings on at the microscopic level, I think it's so impressive that you've balanced it all and still found a way to keep working on the vast Earth observation problems that will challenge us all well after COVID. And finally, I wanted to personally thank you for the last few weeks. I can honestly say it's been the best time of the entire year getting to meet each and every one of you and learning more about your work. Everything that you're working on is inspiring, and I'm so excited for the others to learn from your talks today. And we're super hopeful that you'll make new connections here and continue to share your knowledge of Google Earth Engine with your peers and with us. So how is this going to work? We have 5 rounds, as we've published, right, of amazing lightning talks. It'll be similar to the lightning talks that you saw yesterday. And we're going to play those lightning talks in a block. And then the speakers, once those blocks finish, will be available here for Q&A. Right, so we'll have a little bit of a panel discussion. I'd like the speakers to be able to introduce themselves and ask their questions first, and then I will be moderating comments on the YouTube live stream. So if you have any questions, if you see something you say, wow, how'd you do that? Or I want to know a little bit more detail. A lot of the speakers have put together their contact information, but we have some time after each one of these blocks to be able to have those conversations. So with that, I'm excited to get going. Let's start with our first round of talks. From Australia and the University of New England, James Brinkoff.
Hi, I'm James from the Applied Agricultural Remote Sensing Centre at the University of New England in Australia. This was a project we did using Google Earth Engine to look at macadamia tree area estimation over the whole of Australia. So if you're not familiar with macadamias, it's a tree that's native to Australia, and the area planted has been growing rapidly in recent years. The macadamia produces a lovely nut to eat that you might have eaten. So that's part of the driver for that growing area. So here's a Google Earth Engine web app that visualizes the results of the analysis. And you'll see this is the east coast of Australia. It's separated into different growing regions that the tree area is assessed over, and all the bright green shapes are the shapes of the macadamia plantations that's been produced by a national tree map that's been produced by some of my colleagues at the University of New England. So what we did is for every pixel within each of these macadamia shapes that was imported as a shapefile, we found the Ndvi time series. So the median Ndvi per year from 1988 to 2020 using Landsat data. And so we were able to get a growth profile like the one you see here on the left. And what we observe is that the Ndvi fluctuates. Many of these fields were previously sugarcane plantations. So kind of annual crops harvested and high growth phases during different years. And then at a certain year, the macadamia tree was planted, and that's when the Ndvi starts to have this consistent growth profile, as you see there towards the end of the time series. So this time series was extracted for every macadamia pixel in Australia. Then we were able to work with some of the orchard owners to obtain the actual plant date of their particular macadamia orchards. And so we obtained about 100 data points for that. I'll just go to this one. And from that, we were able to study the relationship between those time series and the actual plant years supplied by those macadamia growers. And so we produced a model by searching through a number of different algorithms to optimize the prediction based on those time series. And this is the results of the prediction for those 100 or 95 orchards there across different regions. The other thing we did was use Sentinel-2 data from the whole of 2019. And this was done because the tree map that we used included many areas such as roads and lakes and houses and unproductive areas. And so we were able to produce a kind of a classification of the actual productive macadamia area within each of these coarse macadamia tree features. And so that's shown in brown there. So the optimum planting date algorithm turned out to be finding the year where the Ndvi crossed the threshold of 0.62 and then subtracting 3 from that year. And so, for example, for this, you see the little blue dot there, that crossed the threshold of 0.62 in 2011. And so the estimated plant year was 2007. I've made a mistake there. Oh, sorry. Yeah, so it's the year before it crosses 0.62, which is 2010. Subtract 3 from that, and you get the estimation of the plant year for which is 2007. And so we can interactively view this. So the red areas in the map are sort of later plant years. The blue areas of the map are earlier plant years. So, for example, if I click on an earlier plant year, it'll go away and it'll get the time series from the Landsat data for that particular pixel. And it's estimated the plant year of that particular pixel is 1990. And you can see the growth profile has shifted to those earlier times there. And so once we had done this plant year estimation for every macadamia pixel in the whole of Australia, we then used Google Earth Engine to aggregate all those results and summed up the total area of macadamias in each of the regions. So you'll see here there's 7 curves in the bottom graph here, and that's each of the regions. From New South Wales inland has the largest area planted, and there's Queensland regions and so on. And so we summed up all those pixels per year, and so we were able to get a time series of the macadamia area and how it's growing from year to year. So you see the green curve is the Bundaberg region in Queensland, which is a rapidly growing area recently. So that's the result of the macadamia plant area prediction app. Thank you.
From Singapore, the natural capital of Singapore, Leon Gaw.
Hello, everyone. My name is Leon, and I am a researcher with the Natural Capital Singapore project. On behalf of my colleague, Dan Richards, it is my pleasure to present our work on tracking spontaneous vegetation growth on Singapore's reclaimed land. So why is this important? Singapore reclaims land from the sea to create space for development. And as new land settles, spontaneous vegetation develops that are in sharp contrast to the manicured landscape of Singapore's public parks. Where is Singapore? It is a city-state in Southeast Asia, located at the southern tip of peninsular Malaysia. Although fully urbanized, there are pockets of greenery found all over the island that is still growing. How we did it is by using Google Earth Engine. We compiled cloud-free multispectral images from Landsat and water, non-water areas from Peckel et al.'s 2016's data set from 1985 to 2015. What we found out is that Singapore's median Ndvi, a measure of vegetation greenness, has increased from 0.3 to 0.6. However, the rate of Ndvi increase is in newly reclaimed lands is faster. Modeling the Ndvi trends on reclaimed lands in our statistical software, we estimated that the median time it takes for a 30 meter by 30 meter Landsat pixel to reach an Ndvi value of 0.7, which was arbitrarily chosen to indicate vegetation maturity, from what was previously water, was 16.8 years. So what do these results mean? After vegetation grows to an Ndvi value of 0.7, they exist for about 23 years before development commences. In this time, they provide ecosystem services such as rustic landscapes for photography and migratory bird havens, and urban planners should consider their transient utility. So finally, I would like to thank the team at Google for creating this powerful tool for remote sensing and the funders of the Natural Capital Singapore project. Thank you for your attention, and I welcome any questions.
From Cambodia and NASA Harvest, Gabriel Seng.
Hi, I'm Gabriel Tseng from NASA Harvest, and I'll be talking about how we used Google Earth and Google Earth Pro to create rapid response crop maps for Togo. Firstly, to motivate the problem, crop type mapping has a number of uses, ranging from forecasting food supplies to understanding factors affecting crop stress. We worked with the government in Togo, who needed a crop mass to better understand where farmers were distributed and how much they were growing. Different countries, even if they're neighboring, grow crops in very different ways. Here's an image from Borneo, an island shared by Malaysia, Brunei, and Indonesia. On the Malaysian side, palm oil plantations are eating into the rainforest, something which isn't happening on the Indonesian side. This heterogeneity makes global crop mapping difficult, as some countries might have very few labeled data points. The Geo-Wiki Data Set is a global data set of 35,000 crowdsourced crop and non-crop labels collected in 2017, which has widely been used for crop mapping. However, it only has 58 labeled data points within Togo. This sparsity means that crop mapping models which rely only on the Geo-Wiki dataset do poorly in Togo. To illustrate, here's an area of cropland in northern Togo. A map produced by Copernicus using a random forest model trained only on the Geo-Wiki data fails to identify any cropland there. We were tasked with developing a crop mass for Togo under considerable time pressure. We had 10 days to generate a map. It made sense to leverage global datasets like Geo-Wiki, but we were specifically interested in performance in Togo, not globally. Given that the Geo-Wiki dataset contained only 58 labeled data points within Togo, we supplemented it with hand-labeled data. Specifically, 6 expert labelers labeled 1,319 training samples, and in order to assess the performance of the model, they labeled a test set of 350 randomly distributed points within Togo. One of the major challenges when creating and using sparse labels is that the data is very discontiguous and doesn't align well with data formats. We were using Sentinel-2 data to generate the crop maps. But the sparse data doesn't align well with Sentinel-2 tiles. In Togo, we would have had to process 2 or 3 Sentinel tiles covering Togo to collect the 1,600 pixel points of interest. And this would have required us to interact with a lot of data which was not of interest for this project, including the entirety of Benin. This problem is compounded by our use of the global Geo-Wiki dataset, which consists of 35,000 crowdsourced labels. In addition, we did extensive data processing on the raw satellite data. We used a cloud and cloud shadow finding algorithm to find the least cloudy pixels in an area in a given time frame, in this case a month. Doing this processing locally would have required us to download all the Sentinel-2 time step tiles for the month when we only care about a single pixel and we only want a single value per month. Integrating Google Earth Engine into our workflow made this data exporting and processing much less painful. Specifically, first, we didn't have to care about Sentinel-2 tiles, since we could define the areas we wanted to export. This allowed us to export patches around the labels, making it easy to export labels from all over the world. Second, offloading the cloud pre-processing to Google Earth Engine meant that we only needed to download monthly data instead of the 5 to 6 day data provided by Sentinel-2, but we still were able to take advantage of the 5 to 6 day data to remove clouds. And also, finally, doing this dramatically reduced the cloud infrastructure we needed to set up and maintain for the project. So it allowed us to focus on what was important, which was developing accurate crop map algorithms. Google Earth Engine allowed us to quickly iterate. So we created the Togo crop map iteratively, generating a map for all of Togo, and then identifying where the model was weak to motivate where further labels could be added. So for instance, vegetation on the shoreline was somewhere where the model had trouble. And so we used Google Earth Pro with base maps, which were Maxar base maps combined with Planet Lab space maps to do the labeling, and then use Google Earth Engine to quickly integrate this data into our model, and also to predict crop maps for the entirety of Togo. This hand-labeled data significantly boosted model performance. So we compared our model to two existing data products, the Copernicus and the GFSAD models, but we also compared our model to the random forest and support vector machines, which these models are based off. The other thing to note is that we were able to produce this map at a 10-meter resolution, which is significantly higher than Copernicus's 100-meter and GFSAD's 30-meter resolution. This crop map was ultimately used to support Togo's YOLIM program, which provided $160 interest-free loans to 57,000 farmers in Togo. But the model, this method and pipeline generalizes to areas outside of Togo. So, for instance, we're currently extending this to Kenya, which is 10 times the size of Togo. This also demonstrates how this technique of offloading the infrastructure to Google Earth Engine is really allowing us to scale the maps that we create. Yeah, so thank you very much.
From India and the Assam Remote Sensing Application Center, Mustaq Ali.
Hi, this is Mustaq. I'm a project scientist working under Assam Remote Sensing Application Center, and my colleague Padmini Kaushik and our PI Utpal Sharma sir. So today my topic for presentation is flood inundation mapping using Sentinel data in Google Earth Engine platform for Kaziranga National Park. So basically that what happens is that every year the Indian state of Assam, which is in the heart of the southwestern monsoon belt, receives excessive rainfall. The existence of long ranges mountain belt in the northeastern frontiers state causes the surface runoff to slow down the vast alluvial plains and causing the rivers to swell up. The mighty river Brahmaputra flows through the Kaziranga National Park and thereby killing and injuring hundreds of animals. Animals adapt naturally to the floods, but when the water hits a certain level, they gravitate towards the safer, higher grounds in the Karbi Anglong Hills. So it's an UNESCO's heritage site that is 430 square kilometers of area. So what basically we are doing is that we are not going for a flood inundation mapping. That is not the objective. We are trying to address a problem that what the government is facing to make the cause of Kaziranga National Park. So they are trying to build highlands in this national park. So during the floods, that they gravitate towards the highlands. So you can see through my screen that there is a problem. The floods happens and they migrate towards the highlands. And it's a lowland, it's a grassland. So mostly due to the floods, animals get problems. They gravitate, and due to the traffic in the highways, that causes accident and problems happen. So it's a big problem. In Kaziranga National Park. So measures are undertaken here, but still the problem lies in. So they are not enough to house all the animals in the park. The annual floods, forcing them to move out of the park. They die due to the flood accidents if you crossing the national highway. And we don't also have a detailed map-based information system. So when we started in January, there was no such measures, but in July this year itself, the government also came up with to build up largest artificial highway. So we are happy that we are helping hands to the government. So we thought of doing with SAR imagery. So we are happy with Google Earth Engine's platform, and then we tried to pull back where we use the Sentinel data, and then using the speckle filters, and then using the samples, and the most important, the classification and regression algorithms to classify the image. So to validate our results, also we use the CWC flat forecast data, and then using the confusion matrix and accuracy matrix. So we thought we will come up with some results which will have benefit to have or suggest the government so that they can build highlands where that will be useful, which are not inundated. So we use the flood. So by looking into the CWC data, we can see in the graph that there is a peak which are like above the danger mark flowing. So that's why we took the month of July and January to set of images. So that will help. And then we use the Earth Engine platforms, that is January 2020 and July 2020. So then we come up with the results that what we have achieved using the card algorithms. You can see that in that July that is mostly flooded, and in the January it is not flooded. So basically, that using the graph of CWC, we come up with some solutions that which are the areas which is not flooded. So that by using other incorporated imageries, we can say that this is the areas we can use highlands, or we can build up artificial highlands. So you can also see that the area underwater in July is more and the area under January is less. So we can see that we are classified correctly in a way. So that is also the accuracy matrix for July and January. So we come with a very small, larger scale map, so that you can see this is the built up and agriculture area, and we have nicely classified using our algorithms, so that it's flooded during the July month, and January it is not flooded. You can see that also near the highway, you can see the grass lowland areas are also flooded. So you can see that there is a dense forest. So we have to find a way where the highlands can be built up. There lies the SAR imagery, which holds a upper hand of multispectral or optical data. We have temporal resolution, and also that we can do for when there is clouds also. So that is an advantage of SAR data. So you can easily see that how the results are classified. So now that we want to conclude, as we don't have much more time, so that's why I went very fast. So our conclusion here is that the results and the findings for the study area are one step forward for achieving the objectives. The approach also suggests that our process to attain the results is in right direction to obtain the final goal. So basically, the Google Earth Engine platform is a very efficient tool that we can do the analytics in very quick time. And then we can incorporate many other value-added data, so that can help to find the solution in a very comprehensive way. So then this has the steps completed opens up new light to the investigated the areas in improved way with modifications in our algorithms. So we say that our algorithms is not perfect because you can see here that you can see the river is flowing, but when we use the classification algorithm models due to the 10-meter resolution, that is not classified. So we have to look into our algorithms so that we come up with more precise classifications. Many new items need to be incorporated in this feature, like digital elevation model, watershed layers, increase sample size with respect to the CWC flood forecast data, because you can see the flood is a very dynamic thing. So what we have taken a sample size is that you can see the graph. Even if we have a temporal resolution, those which have a high peaks of the flood forecast data, we have not get that temporal resolution. So we do not have got the satellite imagery for that day. So that is also a problem. So more importantly, also we need a high resolution data for that sample time. So that's all we can say, that with all this incorporation, Google Earth Engine has given us a very good analytics platform where we incorporate all this and we come up with solutions where we can build a highlands. And in the future, we are going to incorporate all this, and hopefully we can help our government to build this highlands. So that's all I can say that in this presentation. And I'm very thankful that Google has given the initiative, and my colleagues, Padmanabh and our sir, Utpal, that has given this opportunity to present this to this platform. Thank you very much.
From Israel, the Ministry of Agriculture and Rural Development, Karl Greenblatt.
Hi everybody, my name is Karl Greenblatt. I'm a mechanization and technology instructor at the Extension Service in the Ministry of Agriculture, Israel. And today I'm going to talk to you about is my project, which is making Ndvi accessible for farmers. So the problem is we have the farmers and they have their fields, and there is free satellite imagery data, but didn't find any good service that can provide Ndvi analysis good and free and accessible. So after I found out about Google Earth Engine, I started writing scripts. So I started with 5 scripts and I uploaded them into Google Docs, and I also made a YouTube guide so people know how to use it. I also did workshops around the country to give people hands-on experience, and I uploaded more and more scripts until I got around to 30 scripts, and I knew it wasn't good enough. So after that, I started making like an Earth Engine app. So this is how it looks when the users using it in the old version. They have to like play a bit with the code to make it fit for their own area or values. And this is how the app looks today. So as you can see here on the bottom right side, we have the Ndvi scale colors. Red is low vegetation and blue is high vegetation. On the top part, we have the sliders we can move between images. And on the left side here, we have the settings where you can set the date range that you like and play with the Ndvi values. And of course, change layer between Ndvi or natural color or a few more layers. So this is how it looks like. And here we have a cloud. And if we're not sure we have a cloud, we can go here and we change to natural color, as I said. It takes a bit of time to reload, depending on your internet connection. And we can see clearly that we have a cloud or shade, and then that means we can't use that image. Another important thing is that to play with the contrast. If you look at this square blue field, we can see it all blue, and we might think it's completely uniform, which is of course not. So we have to play with those values here, the 0.2 and 0.8. And then the palette, the colors change. And we can see now on the same plot, on the same field, it looks different because the values are the same, but the colors change. So now you can see that the edges on the left and on the right are a bit more greener than the middle, which is light blue. That means we have a higher vegetation in the middle. Most time we can't know the reason for the variance with satellite imagery, but we can know where we want to go, where the farmer wants to go and what he expects to see. In cases like this field in the middle here, that we see this line that is red in the middle, I can assume this is irrigation problem. So of course, each case for itself. I also made it available in the mobile version. So the only difference is that you can close or open the settings, like in Google Maps. A taste of somebody who doesn't know what Ndvi is. Ndvi is a vegetation index, and this app is based on the Sentinel-2 images, which is 10 on 10 meters per pixel, and every 5 days we have a new image. This is a bunch of pictures of a celery field that I visited. So this is on the bottom left here, we see the images that I took. And we have 2 beds here that were run over by a spur in order to avoid getting stuck in the mud. This is how it looks from a drone, and this is how we see it from the satellite. So we can see clearly that there is a correlation between them all. This is images that I got from a farmer who has been using this app. So we can see clearly there is a lower vegetation is in the bottom left side. Also here, so this is caused by irrigation problem. Thank you very much for your time.
All right, awesome. I'd like to welcome our speakers up for some live Q&A. Perfect. James, Harold, Gabriel, how are you?
Good.
Very good, thanks.
Cool. Well, I'll give you a chance real fast if you had any questions, having seen those talks, if you had any questions for your colleagues. And then we did actually get a bit of Q&A from YouTube. And I encourage everybody watching the stream, if you have specific questions, just let me know which speaker you'd like to ask that question to. There's a bit of a delay, so just make it clear. And please, everyone, use the YouTube channel for questions. But amongst the three of you, do you have any questions for each other?
Yeah, I got a question from for Gabriel. That was really interesting, mapping the croplands in Togo there. Just wondered what different types of crops are there, and did you find any challenges when sort of classifying those different crops? Did some classify better than others, for example?
Yeah, so for Togo, we're really focused on crop or non-crop, and also identifying crop type is really hard from only remote sensing imagery. So we don't have good information about that. We did find, as I mentioned, that the model definitely performed differently in different regimes. So yeah, but we didn't, or we weren't able to gather information on how the model was performing for different crop types, just because we didn't have crop type information in Togo.
Thanks.
Great. Anybody else before we go to the audience Q&A? Cool. We'll stick with you, Gabriel. When you were bringing in those Planet and Maxar scenes, I imagine you were bringing them in as Earth Engine assets. I don't know if you caught yesterday some of the new announcements around cloud optimized geotiffs. Would you envision using them in the future to bring in those higher resolution satellite data sets?
Yeah, absolutely. I missed the announcement, but
oh. Okay, cool. And can you tell us a little bit more about how the work directly supported the TOLM program?
Yeah, so the main use of this work was to basically identify the distribution of farmers and help the Togolese government figure out how the money should be spatially distributed. So, for instance, figuring out which districts, how much money each district should be approximately receiving based on how much cropland there was there.
Great. For James, how transferable do you think that the work that was specific from academia is to other crops like cashews, for instance?
Yeah, it's a great question, and we are working with a few other industries, avocados, mangoes across the north of Australia, and so it'll be a topic of future work. I imagine different trees will have different kind of Ndvi characteristics at that 3-year age or that kind of thing. So yeah, it'll require getting more ground data from farmers for the particular crops and modifying the algorithm to suit each crop, I would imagine. Some other work around the world has, for example, I think in California, estimated almond age, but they've been able to find a clear year where the land was cleared. And so you get a very sharp dip in the Ndvi, and pretty much that's the plant year. So there's some papers published on that, but it's quite different in Australia with the macadamia industry. Sometimes there's quite a delay between that clearing and when the trees are planted. So yeah, different methods to find those plant dates.
Yeah, I don't know if you caught the key lightning talks from yesterday, but Andrew Wilcox from Unilever kind of showed similar work where they were looking at the age of the particular palm plantations for palm oil sustainable harvesting. So how do you think that the research is actually going to be leveraged? Like, once you know this, what does that do for the government, and what do they actually implement because of it?
Yeah, I think one of the big challenges in Australia is water security. We've just been through 2 years of the massivest drought for the last 100 years, I think. And yeah, so there's quite a growth in the macadamia industry, and obviously trees have very different water use characteristics compared to other crops that have been grown, such as sugarcane, and they have a consistent demand year on year. So I think one thing is analysing water needs. There's a big dam project at the moment, and so it could guide some of those decisions around how much area or how much volume is needed for that dam. And also other things such as nitrogen runoff into the barrier reef, and also yield prediction. So the tree age data is really important for the yield prediction models as well.
Oh, excellent. We have a live question from YouTube for James. Have you found that there is any use for single image classification, such as spectral and textural characteristics, or is the Ndvi time series the only valuable method?
Yeah, great question. We have looked at just using a single image and trying to find a correlation between tree age and a vegetation index. And it turns out the green-red vegetation index has a pretty good correlation with tree age for a single image. I think that the R² was about 0.7 for those 95 fields that we had data for. So it's a possibility. One challenge is, like, once the tree gets to a certain age, the characteristic tends to saturate, like once the tree's quite mature at 15 years old or something like that. So it's not as accurate for those older trees as using a method that looks back through the time series to find the actual planting date. Thanks, Mike.
Yeah. And then we have a question for Harold as well. Do you get feedback from the farmers? Your last slide there kind of showed, some impact for a particular farmer. So I just want to hear like what that feedback loop looks like, and what are the farmers telling you now that it's an app and not just a collection of scripts?
So part of the problem with this app is that I don't know who's using it and how much. That's something you can solve, but there are farmers who do tell me that it is an improvement, because it's easier. Then I can demonstrate it when I come to them on my smartphone. It's much easier. I don't need to open my computer, and very easy to show it. And some farmers do show me that they got value from it. So,
okay, great. Do they give you any feedback on the app itself, or is it mostly just like, or what they're looking for, anything different that they're looking for? And do you make iterations to the app based on that feedback?
I think most of them not sure what they need. It's like I give them, and I thought maybe I add more features like I had in my scripts, but I don't see that they really need them. So I thought making Ndvi animation series should be good enough. So the case of that is there also an Ndvi chart. So there are more, and I can create more, but I didn't see really great need to.
Okay. And then I noticed, as you're reviewing the actual source scenes, that you do have, clouds to deal with. Have you looked at any of the new capabilities for Sentinel-2 specifically to be able to detect and just filter out those cloudy scenes?
Not yet, but the problem with clouds is that what I understand is it can calculate the clouds for the entire tile, not for a specific area. And if I have clouds in the rest of the west side, and I'm on the east side, then if I do some kind of then I lost the word for it, but I won't see the Ndvi in my area because I reduce the clouds.
I got it. Yeah, you don't want to throw out the good pixels.
Yeah,
because part of the scene is cloudy. I think it'd be worth jumping on office hour today, if you have time before the conference ends up, to talk about that specific problem. And I know there's some great advances that have been done recently specifically with Sentinel-2 cloud cover and taking those out. James, did you have anything to say?
Yeah, I've just recently been trained that there's a new product called the Sentinel-2 Cloud Probability that's available in Google Earth Engine, and that does a really nice job of masking out the clouds. So you could possibly even create a weekly cloud-free mosaic or a 2-weekly cloud-free mosaic using that product. It's really good.
Yep, absolutely. All right. So we are at time where we need to get back into the next round. Does anybody else have any final thoughts or comments? All right. Well, gentlemen, thank you so much for this time. This was excellent. And I did have one other question. I just wanted to say there's a lot of feedback. People are wondering, where do I see this research? Where do I see the data? And this goes for Mustak and Leon as well. Are these published as Earth Engine apps? So I think in general, any after the fact, if you have any materials that you want to share, I can put them on the YouTube channel and also just make them available. But if not, thank you all for your time. It was wonderful. And everyone, thank you. That was our first round. We're going to kick off now into round number 2. from Spain, the University of Cantabria, David Montero Loaiza.
Okay, hi to everyone. My name is David Montero Loaiza, and I'm going to talk to you about water storage retrieval using remote sensing and in situ bathymetric data. How do we do that? We use parameter surface-based bathymetry, where we use the bathymetric data from reservoirs coupled with Sentinel-2 satellite imagery. Our methodology was divided into phases. In phase 1, we did an automatic water classification, this in an unsupervised manner. In phase 2, we obtained the satellite-derived bathymetry using supervised models. And in phase 3, we obtained the water storage joining phases 1 and phases 2. We did this in 4 reservoirs in Spain, all with different water capacities. And let's start. In phase 1, the automatic water classification, first, we just started with an image preprocessing. We just used the 10-meter bands. We calculated the normalized difference water index, and then we did a geographic object-based image analysis approach, where we used the simple non-iterative clustering to create super pixels on the image. Then we clustered those super pixels using the K-means algorithm. And then we selected the super pixels that were water by selecting the cluster with the highest Ndwi value. Here, you can see some of the results in the 4 reservoirs. You can see in blue and black the true positives and the true negatives. And in yellow and red, you can see the false negatives and the false positives. You can see that these are good results, but however, you can see also some false negatives and false positives near the shorelines in the reservoirs. These, of course, are errors, but these errors occurs near the shoreline, and the water depth there is not too deep. So the final error in the total water storage retrieval was not going to be too high due to these errors. Then we pass to the satellite-derived bathymetry, where we first interpolated the bathymetric data, and we used the interpolated bathymetry as our target feature. Then we did the data transformation, and for the prediction model, we used 15 predictor features, where 14 were spectral features and 1 was one spatial feature. We used the 10-meter bands, and we used the cumulative cost that in this case was the distance from each of the pixels to the nearest point in the shoreline. And then we use the Lysander transform and the Rayleigh transform, that are transforms that you can find in the literature on how to estimate bathymetry from satellite data. And then we use 3 different regression models. In this case, we use the linear regression as our benchmark, and we use ensemble methods such as random forest and gradient boosting. We passed for training and for test sets. We use for training 95% of the data, and for the test set we used 5% of the data. Here we can see the errors that we obtained in the training set. For the random forest and gradient boosting, we obtained the best results. In this case, 10.7 meters and 10.5 meters in water depth. And for linear regression, as expected, we obtained a highest error, in this case, 14.8 meters. And in our test results, we can see that ensemble methods were better than linear regression, even reaching errors of just 3.4 meters in water depth. We can also see that there is an error variation due to the water depth. After 60 meters, we can see that the error in all the models starts to increase, and this is due to the absorption and dispersion of water of deep waters. And after that, we retrieve the total water storage. We use the surface parameter method, and we, as expected, see that the ensemble method did a good result, obtained the best results with just errors among 4 cubic hectometers. And we can conclude then that we can use totally Sentinel-2 satellite imagery coupled with bathymetric data to create models to estimate the total water storage. Thank you all. That's the end of the presentation.
From Austria, University of Salzburg, Lorena Abad.
Hello, everybody. My name is Lorena Abad from the Department of Geoinformatics at the University of Salzburg in Austria. Today, I will present to you a case study from our RICOLA project, which investigates the interaction between landslides and rivers. For this study, we used the Google Earth engine to map and monitor landslide dam lakes in Kaikoura, New Zealand. If you want to come back to this presentation or learn more about the project, please follow the links or the QR codes on this slide. So to give you a bit of context, on November 14, 2016, a 7.8 magnitude earthquake hit the Kaikoura region in the South Island of New Zealand. This earthquake triggered over 10,000 landslides and created 200 landslide dams, and they blocked the river courses. Several lakes were formed behind these dams, posing a potential natural hazard to surrounding communities and infrastructure due to the risk of flooding. So with this study, we aim at mapping the dam lakes at different points in time in the area hit by the earthquake over a total of 9,600 square kilometers. So to do so, we analyzed Sentinel-2 imagery from late 2015 to obtain a pre-event overview, and then from December 2016 until March 2020. The launch of the Sentinel-2 missions was somehow contemporary to the earthquake event in Kaikoura, so this allowed us to process in total 536 scenes. And of course, accessing, processing, and analyzing these scenes was extremely useful and possible due to the Google Earth engine. So basically what we did with our workflow is to create 18 monthly median mosaics for a study period. We avoided winter months to bypass cloud and snow coverage. We then took advantage of the spectral resolution of Sentinel-2 and computed a water index, the Ndvi. We used dynamic thresholding, and we were then able to extract water pixels for different points in time. With the pre and the post-event change detection, we identified those new water pixels present on the post-event mosaics and then classified them as dam lakes. Then we used the connected component analysis, and we were able to group these pixels into lake features. And then we computed and analyzed their area evolution. So the key findings that we had was, first, that the Earth engine allowed us for a comprehensive mapping of dam lakes over really large areas. We were able to identify potential risk areas at a glance, with some limitations, but still very powerful. It was particularly interesting in our time series analysis that we were able to categorize lakes according to their spatio-temporal evolution into 4 groups, as you can see in the figure here. So first, we had a constant trend, which may suggest dam stability. Then we had a decreasing trend, which can be caused by which can be eventually lead to dam breaching. And then we had this increasing trend, which can be linked to extreme weather events and heavy precipitation. And this scenario could result in dam overtopping. And finally, we had this variable trend, which can be a little bit more linked to seasonal fluctuations. So overall, we believe that this mapping and the monitoring method that we developed is important for disaster management practices, and it can very good complement and contribute into disaster risk management workflows. So with this in mind, I would like to thank you for your attention. We currently have a paper under review where further details along with limitations of this study are expanded. If you're further interested in the code, please check this study's GitHub repository right here. And here's also my contact information. And I hope I can answer any pressing questions during the plenary. Here again are the links for the slides and the project. So thank you very much for your attention.
From Germany, at the Deutsches Zentrum für Luft- und Raumfahrt, Benjamin Lee.
Good day to everyone. I'm Benjamin Lee from the German Aerospace Center and Global Seagrass Watch. Today, I'd like to share with you our efforts to map the seagrasses of the Mediterranean using Sentinel-2 in Google Earth Engine. Seagrasses are marine plants. They provide many important ecosystem services, such as coastal protection, global fisheries support, as well as blue carbon storage. Unfortunately, we have been losing seagrasses at a rapid rate, about 29% in the past century. So this was established by a landmark study in 2009 by Waycott et al. In their study, they also found that the seagrass knowledge at that point of time is lacking in 3 areas, namely South America, Africa, and Asia. Since then, more than a decade later, one of our best seagrass distribution data set is this UNEP collection. This collection comprises data from different sources and therefore different collection methods over different periods of time. Therefore, this is not exactly a current extent of seagrasses, and it's not as suitable for certain research purposes such as monitoring. As such, our team envisions a seagrass analysis-ready dataset, which would allow us to provide critical information such as the aforementioned current extent of seagrasses to seagrass scientists for their use. In order to do so, we will require much processing power in order to process many satellite images over a large spatial as well as temporal extent. Coincidentally, Google Earth Engine fit these requirements. And so we proceed to classify the seagrasses of the Mediterranean from end to end in Google Earth Engine. This means that we have done the pre-processing, training data creation, as well as the classification fully into the Google Earth Engine system, a full virtual dive. In comparison, our validation data is from external sources that would involve a physical dive into the Mediterranean Sea. So, how much were we able to cover with this approach? Using about 280,000 image tiles, we were able to cover a coastal area of about 56,000 km square, building about 19,000 km square worth of seagrasses. As far as accuracy goes, our seagrass producer's accuracy is 55% versus its user's accuracy of about 62%, suggesting a slight underestimate. Our overall accuracy stands at 72%. So let's look at one of our map. This is a coastline in Bastia, France. Our composite makes out this darker area, which you can suggest as seagrass meadows. And these lighter areas here and here, which we can make out as non-seagrass areas. And this is reflected in our classification map. In comparison, the UNEP dataset will classify what we will have plotted as seagrass and deep water areas as all as seagrass areas. Of course, there are challenges to our approach. Spectral variation is an issue that affects classification on multiple levels. On a regional level, the spectral reflectance in the eastern and western basin of the Mediterranean is sufficiently different such that we could not classify them together. On a more local level, cloud shadows as well as tile borders creates artifacts that need to be better managed. Also, seagrasses in the Mediterranean may grow at depths greater than what a satellite can look into. For such seagrasses below this optical depth, we would naturally not be able to detect them. Overall, our research was an initial success. And if you are interested to know more about it, please feel free to have a look at our application here at this URL. We will also like to we'll also be working on publishing our results in sometime in the near future. Moving ahead, we would like to implement more seagrass science into Google Earth Engine, and this would include carbon stock, change detection, as well as perhaps even species identification. So please stay tuned, and thank you very much for your attention.
From Italy and the Food and Agriculture Organization of the United Nations, Giulio Marchi.
Good day, everyone, and welcome to an introduction on Earth Map and its neighbors. My name is Giulio Marchi from FAO, and here are the names of the colleagues in our small team. So fast backwards, let's see how we have arrived here. Back in 2005, Google Earth was out, satellite images were going mainstream, literally, and they were at the fingertips of everyone after being restricted to a niche of initiates. Another huge step ahead was the USGS open data policy, when in a matter of few weeks, the whole archive was made available for free after having reached prices from $700 to few thousands. Around 2010, Google came up with this idea of Earth Engine, a huge bucket of data with a powerful blender to slice and dice at your pleasure, all free of charge. So all these were giant leaps in putting a wealth of satellite images in the hands of the real users. What I'm rambling about is that in these steps, there is a gradient of increasing availability, but especially in their effective usability. In this, let's say, grand scheme of things, we wanted to give our tiny personal push along, let's say, in the feeling of the digital divide between potential users and the power of satellite data. So we started in 2013 with Collect Earth. That's a free and open source tool for augmented visual interpretation aimed to land monitoring through point sampling. Collect Earth connects Google Earth, Earth Engine, other sources of very high resolution images such as Bing Maps, Yandex, and others, to display the same plots in a dashboard of various images and dates, and it allows for multi-temporal land analysis. It was funded by the German Ministry of Environment, just as Earth Map, and Collect Earth has been used in projects from FAO, World Bank, IFAD, USGS too, just to name some. And the collaboration contributed to the signature of a memorandum of understanding between FAO and Google in 2015, renewed in 2019. The most interesting applications also ended up in major publications, such as a couple in Science and so on. But still, since 2014, we had an idea about an online tool for the quick visualization and analysis of environmental and climatic parameters using actually Earth Engine. And here we go with the Earth Map. The idea is to have a sort of shortcut, a code-free graphical interface to access the most used analysis for environment and climate. In Earth Map, the user can select a predefined area of interest or create or upload one, and select and display satellite products, such also as Sentinel-1 and 2, from the left frame, or pick additional parameters here on the right frame to create on-the-fly multi-temporal graphs that otherwise could take days to be produced. Data come from Earth Engine as well as other free sources, and the processing power is totally on Earth Engine. The development is demand-driven, and Earth Map has been already applied to several projects from FAO, World Bank, Green Climate Fund, and so on, at different phases of the project, so from design, monitoring to final evaluation. So we also have a help center with tutorials, frequently asked questions, and a contact us section. Now, for even a quicker approach, we created and synced also an Earth Engine app, where the user can analyze the very same area through a swivel interface to compare two different satellite products on 2 days. The app is accessible from Earth Map directly or through the link you can see here. Now, in the meanwhile, under the new Director General, FAO has developed a special initiative called Hand in Hand, including also a Geospatial Portal. And the portal should take, let's say, a pivotal role in aggregating data produced in FAO from partner organizations, public providers, UN, NGOs, private sector, space agencies, and so on. So for us, of course, it was a no-brainer that the Earth Map and the Geospatial Portal had to be interconnected to allow users to analyze the same area in the two tools, so just with a click. After the official launch at MAP last month, the system are going towards stricter integration, and we are going to have a much more integrated system among the two systems. Sorry for that. So, free data availability is just the foundation. Accessibility and ease of use are crucial ingredients to bring analysis and information to a much wider audience. And anyone can perform analysis with these systems on a wide range of parameters at several project phases. So the suggestion is try it at home. You can keep updated on our Earth Map website, on the Open Forest page on Twitter. We also go Facebook, or you can contact us to suggest new features or new data sets. Thanks for watching. Thanks for the Earth Engine team for the support.
From Canada and McGill University, Lucy Liu.
Hello, everyone. My name is Lucy. I am a PhD student from McGill University, working with Dr. Brian Robinson. So I use Earth Engine to answer a development economics question. Does land tenure influence land use intensity? And in order to answer the question, I worked with Inner Mongolian herders to map out their land parcels. And I then used the land parcels, just like the blue polygon that you see here, to extract data from Earth Engine. A challenge of doing mapping in semi-arid ecosystem is that you cannot see the land boundaries very well in default real-colored base maps. But we can take advantage of other bands. For example, in the winter, snow accumulated on the fences, just like dry grasses. So, which helps us to delineate the land boundaries if we are looking at the image in shortwave infrared. Similarly, different land use intensity also left a different amount of biomass on the ground. So we can highlight this contrast, biomass contrast, among parcels by using imaging near infrared. So when I was conducting my fieldwork last summer in semi-arid region of China, I conduct participatory mapping with herders using customized near-infrared and shortwave infrared image instead. And this method actually allowed me to collect quite detailed data. For example, all the parcels that you are seeing here were identified by herders that I surveyed. We now know land parcels are used during different time period. The yellow ones are used in summer, while the green ones are used in winter. Land tenure is also different. The dashed polygon indicates it's a land parcel being used under short-term contract, while the solid 9 polygons means they are under long-term contracts. So I think a key technical difficulty here is how to make the customized satellite image in a form that can be easily understood by herders. From my own experience, I think 3 elements may foster better understanding. First, it's simply a GPS point that's showing herders where they are on the map. Second is a measurement tool that allows us to validate herders' response. So we can ask them questions such as, how big is your land parcel, or how far it is from the house, from your house to the fence on your southern side. So we can validate, we can compare their response with our own measurement to make sure we are talking about the same land parcel. Thirdly is also where Earth Engine, I think Earth Engine can be helpful here, is to make multiple satellite image scalable so that herder can zoom in and zoom out on the mobile device. For my own fieldwork last summer, I have to convert individual satellite image into individual tile, which can be very time consuming when you are looking at a larger area, multiple dates, and different band combination. So I think a field-based application that has these 3 components, maybe adding the function of recording polygons, could make a valuable tool for collecting field data. I've already finished my data collection for my current project, but I'm still exploring the potentials of making this into future ones. I'd be interested in thinking forward about this with anyone who also find it useful. Thanks.
Wow, those are awesome talks. Thank you all, and please come on up. David, Lucy, Benjamin, Julio.
Hi, Jen.
Oh,
Hi.
Great to see you all. Wow, and you're all here. Perfect. So just like the last time, I'd like to first open up discussion amongst you all if you had any questions after watching your colleagues present. And then if not, I've got a large number of questions actually that have come in.
Maybe we can go with the large number.
Sure, good. And Julia, we'll start with you. So you've really taken the concept of no-code Google Earth Engine very far, and you mentioned demand-driven development. So what do you see on the horizon, and what is missing from Earth Engine that could help you, if anything?
All right. Those are two very separate questions, actually, because what we see on the horizon, it depends on the project we are involved with and the activities, the external activities we're involved with. So we actually follow what, I don't want to say our customers, but our, let's say, users actually desire. So the new additions, the updates, the new features in Earth Map literally follow what the users need. How to have, I mean, we have a lot of ideas. We definitely have more ideas than human resources, and that's maybe the issue. So, I mean, I don't want to do the list, but there are several major features coming, and just stay tuned. What we would need from the Earth Engine side, all right, that's a long list. And since Christmas is arriving, maybe I will wait a few months for that. Because so far the support has been great, but of course, maybe this is not the right, let's say, time and especially time length to discuss about this.
Okay, fair enough. I do have two other questions though. Were there any challenges with integrating with the hand-in-hand platform, or like not just technical challenges, but like different goals that you may have had to overcome?
No, the parallel is going. The development is going basically in parallel and converging, because actually the needs sometimes are overlapping. And since they had, I mean, the Geospatial platform is a more, so to say, institutional platform for FAO. So they set the pace for the organization itself. We, let's say, belong to our project and we refer to other activities. So the context and the scope is a bit different. But having said that, once we set the possible joint purposes, what we would like to see very soon is a strict integration. So let's say the same area can be analyzed from one platform or another, really seamless for the user, because we don't want to, let's say, to have the user be involved in any, let's say, coding or even complex procedure. So a more seamless transition from one platform to the other is really to be expected in the next weeks, and we are literally discussing it in these days with the colleagues.
Great. One last question for you. In our last block, Harold from Israel mentioned some challenges in terms of getting monitoring usage of his application. How have you handled that? How have you managed to monitor usage and maybe understand impact of what you're delivering?
Well, the usage is partially monitored by our developers, but so far we are not really, let's say, interested in the usage, because we are already a bit overwhelmed with requests, so we don't really need to know who else is using it for what. I mean, EarthMap is there for free for everyone to use it, thanks to Earth Engine and the support of our funds, that is the German Ministry of Environment. And anyone is welcome to use it, but especially to provide feedback in terms of new possible data sets or new features or possible bugs that, of course, are there and we still have to squash.
Great, thank you. David,
Yes.
Question came in. Does turbidity influence your bathymetry data?
Okay, sorry, Shane, I didn't hear the question.
Question was, does turbidity influence your bathymetry depth results as part of your input?
Okay, sorry, Shane, I'm having trouble. Okay, again,
No problem.
please.
Can you hear me?
Yes, but there is like interference.
Okay. The question was about turbidity and if that influences the depth.
Yes, that's right. Because in some areas where there are rivers that are contributing to the lake or the reservoir, there are turbidity, yes. And in the case that we were using the NDWI is susceptible to the turbidity. So in some cases, false negatives could be caused exactly by the turbidity there.
Okay, and following up on that, Scarlett just asked, your method is only suitable for shallow water. What do you do for deep water bodies, which also I think it's going to tie into a topic that came up with Ben.
Yeah, exactly. Yes, maybe just for shallow waters, more or less 15 meters in depth, because more than that, as we can see in the presentation, the error starts to increase. So it's better if you know that the deep water, that the depth of the water is more than that, not use it in that way.
Got it. Okay. Sorry to go over here to Laura. So loved the work, especially the crisis response aspect of it. And there was a question, Lorena, for is the sensor data for the lakes? Is there any sensor data on the ground that's being used to calibrate or ground truth your remote sensing methods? Oh, David, I'm sorry. This was for Lorena.
Oh, okay, sorry.
No worries. But if you also have sensor data, that would be great. So not really that we're aware of. So what we basically know is that there are locations. There's a data set with locations of these dams. So these we use to validate our basically our mapping results. So to locate the lakes and see that they were where they were meant to be. This is from the GNS in New Zealand. But really having like a lake area or lake volume already as sensors and giving us data that we can corroborate our time series and our time lapse, there's nothing available that we are aware of out there. So that's why we think that what we developed is quite complementary to all the monitoring efforts. Also because only few lakes are really being monitored because these are the ones that pose major hazards. But there are other lakes that maybe it's not even in the public knowledge that they are there or if they pose a hazard or not. So they're also interesting to look at probably. And this is why we think that our monitoring workflow would contribute to that.
Yeah, I think your categorization methodology there is really good too, right? Like here's the high risk ones, et cetera. How do you get that data to the government? How does New Zealand consume that, or are you trying to go direct to the local population?
Well, what we would like to do is indeed to have some interaction with the government, indeed, especially with this crisis risk disaster groups that are in New Zealand. And that would be great, actually, if we could have a little bit of context. So maybe through here we can do some bridging and diminishing this gap. But of course, what we also want is that this is freely available for everyone in the public. There has been a lot of work done around this Kaikoura earthquake and all the effects that it's had in several fields. So we think that putting it out there and putting it public is a way that people can also be aware of this and use it in wherever ways they need and complement their own data needs. So hopefully an application and Earth Engine application will be out soon. And that would also make it easier for people who are not so into the coding part to also take a look at that.
Yeah, it seems like we're like ultimately like kind of all heading towards the same reality, which is we have all this massive Earth observation data. It's really good. The tool makers have come along and figured out how to exploit it, how to turn it into intelligence and knowledge. But ultimately, like an end user, just like needs to know, hey, don't drive here. There's a fire outbreaking, and it's like that end result is a couple kilobytes, right? It's a polygon that makes an influence in a person's life and sends out a warning to say, hey, there's a risk of a flood here. So I think that's a common theme when you look at humanitarian disaster response uses for this Earth observation data. For Benjamin, as you look to expand into the unmapped regions of the world, the accuracy was 62% for the existing models. Did you find that the UNEP WCMC was unreliable for calibration purposes?
The dataset for the UNEP covers over a very large range. We can get data as old as about, I think it was 1930s or 1960s, I need to recall correctly, up to about 2000 plus. I mean, the bulk of the data was in the 1990s or 80s or so. So if we were to use a UNEP dataset, we need to know that the dataset is not as updated as we think it is, because they rely on a lot of historical data. So right now we have the power to use remote sensing to be able to estimate some of these seagrass areas. And our idea for this analysis-ready dataset is similar to that of global forests, global intertidal, and so on and so forth, to create an analysis-ready dataset that can be used over multiple years, and which allow us to compare between times, and it's a lot better than something which is compiled and collated over time, and you can't really tease out whether it's there or it's not there anymore, and so on and so forth.
Got it. So we are running up against time here. So I want to jump over to Lucy. I loved the delineation using SWIR to detect snow on the fences. I just think that is so cool, as well as also looking at the land disturbance as well, because in so many areas of the world we don't have really good parcel data. We don't have really good cadastral data of understanding, how land is actually used. So I thought that was really great. And I also thought it was great how you ground truth that in the field to understand the seasonality behind there. So ultimately, though, now that you have this understanding, what is the impact for the herders, and then how does the government leverage your results?
Yeah. So, I mean, before I go to fieldwork, many people told me that herders may not able to recognize the maps. But then when I realized that if you giving enough time, that allows communication, allows we to identify multiple figures, that because herders, they use navigation on their phones. They also, so herders themselves is interested in interpreting the maps. So I see many of them are interested in. And then, from the government currently, they are mapping land parcels using GPS and drone, which is highly accurate, but also takes a lot of human resources and time. So I think if these can be offered as an extra tool for them to use, it will be good. But I think it's still in the planning stage currently.
Well, fair enough. Well, thank you all. Any other questions or comments before we transition into the next block? I really, again, wonderful talks again in this round, and thank you so much for the time and the research, and hopefully you're able to continue to make connections. I love, by the way, that James, I know it's late for you in Australia, but James is sending in questions here, so please do stay on. I think that's so cool that we're starting to build some connections and networking here. Anything else before we jump into the next round? All right. Well, thank you again. And just so everybody knows, as a programming note, we are going to do this next block. We will then have the next block's Q&A. But after that, we will take a short break, just to kind of break up the day just a little bit, give everyone a chance to grab a drink or something like that. So here we go. We're going to go into round number 3. From the United States of America and NASA Goddard Space Flight Center, Liza Goldberg.
Hey everyone, today I'm really excited to present some recent results looking at the global distribution of both human and natural and climatic drivers of mangrove forest change, both across the world and also in marine protected areas in particular. My name is Liza Goldberg. I'm a student researcher at NASA Goddard Space Flight Center, and I'm also a freshman at Stanford University. So first, why mangrove loss drivers in the first place? So in these two images, before and after 2004 to 2020, you're looking at here, some pretty extreme examples of conversions of mangroves to shrimp and aquaculture ponds in Sulawesi, Indonesia. And what's so significant about this example here is not only the extent of the losses that we're seeing in this region, but also the fact that these losses are occurring within a level 1A IUCN protected area, which is actually the highest level of international protection. So clearly these sorts of localized extinctions of mangroves due to these human-driven conversions still continue to be common throughout Southeast Asia and around the world, and specifically within these sorts of marine protected areas in particular. So this project was really driven by the idea that we need to get a better understanding of both which losses are due directly to human factors and which are due to more natural or climatic drivers. And further, what are some lessons that we can learn in terms of marine protected area governance to ensure that these sorts of human-driven hotspots don't continue to occur within protected areas in the future? So jumping into some of our global results, looking at the global distribution of human and naturally driven losses from 2000 to 2016, we found that about 60% of all global losses were due to these anthropogenic conversions from mangroves to aquaculture, agriculture, or things like settlements or through clear cutting. And we found that Southeast Asia was actually a pretty significant hotspot here. Over 80% of all conversions of mangroves to these human-driven factors occurred just within 6 Southeast Asian nations. And further, when we kind of narrow that down to just conversions to aquaculture and agriculture, we found that over 95% of those conversions were occurring just within these 6 Southeast Asian nations. However, we do actually have some good news for you. If you look at the left panel of this chart here, between 2000 and 2016, we saw a 73% decline in total mangrove losses across the world. And more interestingly, by that last epoch, we actually found that there's almost an equal proportion of losses due to both human or naturally driven factors. So definitely some good news on that front. Actually, if we take Southeast Asia out of the equation completely and look at just losses outside of these 6 Southeast Asian nations, by that last epoch from 2010 to 2016, we found that the vast majority of losses were actually due to these natural drivers, not human-driven conversions. So what's actually driving this trend? Part of it is because over the last 2 decades, we have seen a pretty substantial increase in interest in conservation and restoration efforts for mangroves on the national and global scale. So at least in some of these regions, those conservation efforts are effective. But on the flip side of things, especially within regions like Southeast Asia, we're finding that in many cases, there are essentially no more mangroves left to lose. We've lost so many mangroves due to these conversions to aquaculture, agriculture in the past, that there just simply isn't enough viable area for these sorts of conversions to continue. So which of these kind of 2 scenarios is it? That's going to depend on local and national policy, and something that we're interested in looking at in the future. Narrowing it down to just protected areas in particular, in this chart, in this graph, you're looking at the percent of national human-driven losses that are occurring within protected areas across the world by mangrove holding nation. And what we're seeing here is that instead of Southeast Asia, it's actually the Americas that's the anomaly here, in terms of the fact that, at least in some of these cases, almost all human-driven losses across the country are actually occurring within just protected areas. What we're also able to look at is the distribution of human-driven loss within the protected areas themselves. And here we find that the vast majority of losses are occurring within just in a 1,000-meter buffer from the protected area edge. So people aren't really venturing far into the protected area itself in order to do things like conversion to aquaculture, agriculture, or clear cutting. We can see that that varies slightly with the West Africa scenario. However, with conversions continuing to occur as we get farther and farther within the protected area. So now that we've kind of seen an overview of some headline statistics that we're looking at globally with these sorts of analyses, I definitely recommend checking out Mangrove Loss Drivers, that app, in terms of both reading the paper that we recently produced on the subject, looking at a recent Earth Engine app, that lets you explore the data and also analyzing some user-generated scripts to explore the data on the local to national scale. And with that, thank you very much.
From the United States of America and the USDA National Agricultural Statistics Service, Dave Johnson.
Hi everyone, I'm Dave Johnson with the USDA's National Ag Statistics Service. I'm going to talk very briefly about real-time crop mapping within the Earth Engine environment. So our goal with this is to generate crop type maps within season using Landsat and Sentinel-2 imagery and also historical USDA cropland data layers. We're really trying to leverage those tools and data sets within the Earth Engine environment. We want this applicable to the whole USA. We want to be able to integrate the very latest imagery as it dumps into the Earth Engine catalog. This needs to be accessible to anyone. And a big point to note is we're not trying to use any training data from the current year. We're only leveraging the historical CDLs for training data. I'm going to focus in on an area in Montgomery County, Maryland. It's actually where I'm talking to you virtually from. I have an area in red. That's where we're really going to focus in. So we're just northwest of the Washington, D.C. area. And yeah, as you get about 10 or 20 miles outside of D.C., you do run into corn and wheat and soybeans. Here's the cropland data layer on that focus area in 2017. I've got highlighted in a blue oval, a large cornfield. Yellow is our color for corn in the CDL. There's a picture of that cornfield in the middle of the season, or probably around August. In 2018, that field was soybeans depicted in the darker green. There's a photograph from early in that season, small soybean. Then in 2019, the cropland data layer showed a cornfield, and there's a photograph also from 2019. So with this in mind, the question is, what happened in 2020? So one way we could get at that is to just purely look at the past CDLs, knowing there's a strong crop rotation pattern across much of the United States. So, you know, just to summarize it, we're letting the decision trees through a random forest classifier generate those rules, and we're going to apply those rules to this year. When we do that, for 2020 prediction, the area in the blue oval, which I've been highlighting, models out to be a soybean field, and that's what I would have guessed also, but unfortunately it was actually a cornfield this year, so missed on that field. So another way we might look at this, hopefully provide better information, is Landsat imagery. Landsat is available within Earth Engine, of course, and the Earth Engine stages the surface reflectance, so we're really trying to adjust for atmospheric effects. So this has been great. So the idea here is we can generate composite images through the growing season. I've chosen a 48-day time window. So not only can we do that for this year, but we can do it for years past. And then those past years, we can intersect with concurrent CDLs, draw samples, generate decision trees, again, through random forests, and apply those to this year's data. Here's some quick screenshots of composited imagery over that area, Landsat. This is roughly late April, mid-June, late July, and finally middle of September of this year. When we put those together, and with the assumption of imagery through October 1st, we have classification looks reasonable. At least our area of interest is coming out as corn. If we limited it to data only through May 1st, then the classification is very rough. So same idea, but using Sentinel-2 data. Advantage there is a 10-meter product now versus 30. But we don't have quite the history yet because Sentinel-2 data only appears 2016 to current. But Sentinel also gives us a better revisit rate, so we can have shorter time windows on those composites. So here's April 21st, late May, mid-July, late August, late September. That classification using data through October looks excellent, and you can see finer details spatially as well. We only do it through May, it's pretty rough, so it's still not good. Finally, we can throw these all together. Landsat, Landsat, the modeled, and Sentinel-2, use the random forest, and if we do that, we get a very good classification through October. 1st. Rougher if we just do May 1st. Finally, within our own section, we've been producing the 2020 CDL, so we can look at the agreement between what's being produced in Earth Engine versus that. And the short answer or short note here is the imagery really helps us in the middle of July and produces a classification better than just the rotational aspects only. So in conclusion, is Earth Engine up to the task? Absolutely. And this is working. Is it perfect? No, but it's very useful for many applications. It's easy to run. And I suspect when we get a deeper Sentinel archive, it's really going to improve. And are we going to run this nationally? And absolutely. So thanks.
From the United States of America and the United States Geological Survey, Victoria Stingle.
Hello, I'm Victoria Stingle, and I am with the USGS based out of Austin, Texas. Thank you for the opportunity to present our work in Earth observation monitoring of harmful algal blooms in Texas reservoirs. Harmful algal blooms and cyanobacterial blooms, collectively referred to as HABs, cause water quality and ecological problems across our planet, including human, pet, and wildlife health risks. These risks include acute and chronic toxicity, anoxia, taste and odor problems, and fish kills. Current ground monitoring, data collection, and analysis of water samples often have a minimum of several days before results are available. And unfortunately, these effects of harmful algal blooms often serve as the indicators that a bloom is occurring. In collaboration with North Texas Water Supply Reservoir Managers, we are developing a water quality monitoring system that ingests imagery from Sentinel and Landsat 8, Sentinel-2 and Landsat 8, and is powered by Google Earth Engine. The system is being developed to help identify HABs in near real time and to study temporal trends of bloom activity. This is the very high level overview of our system that has a lot of moving parts. But the big picture is to convey here how our in situ water quality data collection fits in with all the moving parts. So we have multiple sites on multiple reservoirs. Right now we have about 14 reservoirs, and the number grows because we respond to active blooms if and when they occur. These data are used for calibration and validation at multiple stages in the process. So the big picture is ultimately spinning up the deep stack in Google Earth Engine. We're working on ingesting imagery with aquatic atmosphere correction applied. And then we move through the processing of, for example, using cloud filtering and cloud masking. Currently, we are working on producing the chlorophyll concentration probability maps, where the data are used to test performance of spectral indices at each sample site. And once we have the indices selected, we will generate spectral vectors, time series vectors, revealing temporal variation at each site. And ultimately, our system will be delivered to the public in near real time in a web mapping application. So our in situ water quality data collection is conducted by a team of biologists and ecologists in our North Texas office. They coordinate sample collections with satellite passovers on, or satellite overpasses on sunny days. We collect signatures from boats using spectroradiometer with a collection of water quality data parameters, including chlorophyll and phycocyanin concentrations. Our in situ data collection study design includes, each lake includes a deep water sample site for pure pixel calibration. And in addition to that, there are sites that we've selected near confluences of tributaries to explore the variation of these dynamic systems and the spectral variation of the systems. And we've utilized a suite of tools that is delivered in the Google Earth and Google Earth Engine paradigm to explore the temporal variation. And I've included a example of using the Landtrender Earth Engine app where in order to select these sites, I generated a number of spectral indices to understand the behavior of these locations on the lake. So in order to conduct essentially the magic of remote and the science of remote sensing of chlorophyll concentrations, we have extracted a number of spectral indices from the literature, and we're using a multiple lines of evidence approach in collaboration with the Idaho Water Science Center. And ultimately, the spectral indices are evaluated against the in situ chlorophyll concentration to determine index performance at each site. And if anyone has any questions, please feel free to reach out to me. Thank you again for the opportunity to present.
From the United States of America and the U.S. Forest Service, Josh Heyer.
Hello, my name is Josh Heyer. Thank you for attending my virtual talk on a big data reduction workflow for remotely sensed imagery. I'm an on-site contractor for the Geospatial Technology and Applications Center with the Forest Service in Salt Lake City. I'm excited to share this workflow with all of you, and if you have any questions, feel free to reach out to the email provided here on the title slide. I'm really just scratching the surface of this workflow, so I'm more than happy to entertain any questions. So our objective was to automate a workflow that efficiently collects large quantities of Landsat and Sentinel-2 imagery, masking spectral anomalies from the collected imagery and generating annual image composites at a spatial extent that optimizes image size and export time. And so how do you optimize the collection and processing of large remotely sensed image collections? And for our purpose, we're talking about composites, annual composites, all the way from 1984 through 2020. And to do that, and for the continental US in our case, and to do that, we subdivide the United States into tiles, and then we use the Python Earth Engine API, as well as modules, the GVIS module, a repository that has modules to optimize the processing and collection, and as well as using pre-computed cloud scores and shadow masking statistics that are stored in Earth Engine assets. And so this workflow is transferable to other areas of the world. However, for our purpose, we use the continental US. This is our focus. And so you can see here that we subdivided the continental US into tiles. And this just ensures that processing in Earth Engine is possible, and that the image sizes are manageable once you export it out to a local drive or use it elsewhere for modeling or other purposes. So this is just a flow chart or a conceptual diagram of our workflow. And like I said, I'm just scratching the surface. So there's intricacies and nuances within this workflow, of course. So you define your tile or your tiles within your area of interest. Then you can collect. On the left, you see Landsat imagery for the growing season. And on the right, you can collect your Sentinel-2 imagery once it becomes available in 2016. And then you can join the Landsat imagery surface reflectance and top of atmosphere for FMAS, cloud masking. And then for both Landsat and Sentinel, you can use the pre-computed cloud scores that we store in Earth Engine assets to mask out clouds. And then you merge those collections together, and then you run the shadow masking algorithm. And those statistics are also stored in Earth Engine assets for the entire continental US. And storing those in Earth Engine assets really speeds up the processing time. So next, what we do is, here's another conceptual diagram. And I'll mention here that we use as I mentioned, the Python Earth Engine API and GVIS modules to make all this processing possible. And so Next, we generate metaweight composites on an annual pixel-wise basis, annual composites, and we store those in Earth Engine assets. And then using those composites stored in Earth Engine assets, we generate land trender fitted composites and store those in Earth Engine assets. And all this is done on a pixel-wise basis. And finally, you can use these land trender fitted composite bands and indices and land cover modeling. Here's just an example of the products and applications. So on the left is a product, a fitted metaweight composite, land trender composite, false color image. And then you can use those band values and indices to do things like predict tree canopy cover. On the right, you see an application. So this is tree canopy cover predicted for 2019. And so a few recommendations is for big data workflows to be possible. We really recommend and found that using the Python Earth Engine API is needed, and as well as GViz modules that we've developed at GTAC. You can check out the Get Images lib and Change Detection lib specifically that are stored in GViz at the following link in GitHub. We also recommend you consider cloud and shadow masking algorithms that we use. They did a great job of masking algorithms for each annual composite. There's a article there that discusses these algorithms a little bit. There's supposed to be a methodology paper up and coming that should be coming out soon. And then really using pre-computed cloud scores, TDOM statistics, as well as composites. If you have space in Earth Engine assets, that can really increase process or improve processing speed if you just run those and then store them in Earth Engine assets. Finally, another recommendation is the Julian day range is important. This can influence artifacts found in your composites. For example, snow, if you use too early of a range, you can have snow, or if you use too narrow of a range, you can get clouds and shadows, something to consider. And if your image acquisition is for many years like ours, and for large AOI like ours, if you can get premium Earth Engine credentials, that really helped us improve processing times. And if you can get additional space for assets, that is also recommended. Just to make all of this possible. And so I blazed through this presentation. There's a lot more I could discuss. Like I said, I just scratched the surface. I have, during the question Q&A coming up in a few weeks, if you have any questions on the metaweight process or the land trender composite, land trender fitted composites, I have supplementary slides I can show you. And I can discuss those processes more, as well as any of these modules in GitHub and the GViz module. So with that, I'll thank you for attending my virtual talk, and I look forward to any questions that you have for me in a few weeks, and feel free to reach out to my email provided here on this slide or the title slide for additional questions and follow up if you're interested in this workflow or the modules that we've developed. Thank you.
From the United States of America and the University of Tennessee, Chusung Wu.
Hello, my name is Chusung Wu. I'm at the University of Tennessee. In this presentation, I'm going to introduce the Gmap package for interactive mapping with Google Earth Engine. The slides for this presentation can be accessed by scanning the QR code or visiting the URL at the lower right corner. And here is the outline. First, I'm going to introduce the package and how to install it. Then I will show you some video tutorials. And lastly, I'm going to demonstrate some of the key features of Gmap. On the right here is a Landsat time-lapse animation created using the Gmap without writing any line of code. You can click the link here to open the web app in your browser, and then you will be able to navigate to any location around the globe and to just simply draw a rectangle, and then you'll be able to create a time lapse and download it to your computer. You can also click the notebook to see the source code behind this web app. So let's dive into it. So what is Gmap? It is essentially a Python package for doing interactive mapping with Google Earth Engine and IPy Leaflet and also IPy Widget. It is open source, hosted on GitHub. You can see some of the key dependencies in here. And it can be used with the Jupyter-based environment, such as Jupyter Notebook or Google Colab. And you can install using pip, conda, or directly from GitHub. And on the right here, I also have a tutorial showing you how to install. And if you see from the animation here, you only need one line of code to create an interactive map, and then you can start doing loading Earth Engine data. Here shows you 2 examples. So you can be using Google Colab and also Jupyter Notebook. Keep in mind, Colab currently does not support IPyLeaflet, so you need to use the Folium backend. If you're using Jupyter Notebook or Jupyter Lab, then you can use the IPyLeaflet. So you can click on the left side here, notebook template, also video tutorial to how to use this with Colab or Jupyter Notebook. Also published a short paper describing the package. You're welcome to check out the link for more information. And I also created a website, API documentation. So you can click the link here to check to get more information. You can also look at the API documentation to see the source code behind each function. And so next, I'm going to show you some tutorials. I have created a YouTube channel just to share the videos for this package. And so far, I have created 37 tutorials with a total length of more than 9 hours. So you are welcome to check out my YouTube channel for more information. And here's the list of all the tutorials so far. For each tutorial, I have a full-length video, usually 15-20 minutes. I also have a short animation, less than 1 minute. I also have a corresponding Jupyter Notebook so that you can reproduce exactly what I did in those tutorials. So lastly, I'm going to demonstrate some of the key features. The first one is you can do automatic conversion from JavaScript to Python directly within Jupyter Notebook. So it saves you a lot of time if you're trying to do the conversion. You can search the Earth Engine data catalog by simply typing a keyword and then one click to import the data to Jupyter Notebook, and then you'll be able to load the data onto the map. So very easy to do. You can use the inspector to interactively inspect data layers. So you can just click your mouse on the map and then to query all the values. You can do interactive plotting. For example, simply select the layer and then you can click your mouse on the map to plot the spectral scenes. So for example, spectral data or hyperspectral data. You can also have a lot of base map to choose from, a lot of XYZ and WMS web services from the internet. So you can choose a lot from the drop-down list. You can use one line of code to create a split panel map. Was one line of code, easy to do. You can also load a local data set, for example, Esri strat file from a computer, and then convert it to Esri, convert it to Earth Engine objects. You can also load local raster dataset. So, for example, you have GeoTIFF on your computer. You can load it, and then so that you can compare the dataset with Earth Engine raster datasets. And lastly, you can convert your Jupyter Notebook into a standalone web application using Voila and some other open source packages. You can also deploy into your server. So in that way, you can share your final product with the general public. And lastly, I would like to welcome your contribution to the package. And you are welcome to check out some of the links in here. You're also welcome to join the Slack channel for live discussion. Okay, thank you very much for your attention.
Sorry, I was muted there. Wow. That was another great round. So much information flying in, and we have a ton of questions actually that have come up for that particular round. So please bring up our panel of amazing speakers, and thank you all. Thank you all again for your talks and for being here live today. As we've been doing, I wanted to first open it off to you, see if there was any cross-pollination, if there was anything that stood out from other folks' talks, if you wanted to ask any questions before I go to what's been submitted from the audience. All right. Liza, I'll start with you. So thank you again for this. I know you've been working on this mangroves monitoring since high school. And it's so inspiring, by the way, that you've been involved in this since high school. And now you're published. The work is fairly mature. You've got the app, Lost Drivers app, published. So what's next on this project?
Sure. So thanks, Sean. That's a great question. I think what we're really moving towards now is trying to get at the dynamics in protected areas across the world. I gave kind of a general overview of where we're going in terms of some initial statistics and analyzing the effectiveness in global marine protected areas at preventing these sorts of human-driven losses. But what we're also interested in doing is starting to bring in gains into the picture there to get overall dynamics and net change that we're seeing. in all mangrove holding nations across the world, specifically in these protected areas, and then ultimately giving that data to several different conservation organizations that we're working with to see how that could potentially inform sustainable conservation practices in the future.
Yeah, that was actually going to be my next question. Like, how do you think you actually influence further the reduction in those conversions that you see? Is it primarily NGOs? Is it government? Like, how do you think, what's been most effective?
Yeah, so we're currently working with several different governments and universities, specifically in the East Africa region, and looking at, where have we been in the past in terms of what the extent of those human-driven conversions along coastlines, and where are some of the hotspots that we need to focus future conservation efforts moving forward. And that is kind of what was driving the whole marine protected area analysis. We found that those areas were potential hotspots where potentially decreasing these sorts of large-scale human conversions was definitely viable, and so that's why we're kind of shifting our analysis towards that in the future.
Great, Dave. Lots of questions came in. First question was, how generalizable would the RF models be? Would you need one for each state or county, or do you think it's something that could be applied nationally?
So I showed the example from Montgomery County, where I live in Maryland, but the effort is applicable nationally at a county level. So one would choose a county. The county is a nice size because it's Earth Engine can handle the performance where you don't get frustrated with having to wait a long time. But also you wouldn't want to take information from a cornfield in Florida and apply that to the state of a cornfield in Washington. So certainly you want to constrain your geography somewhat for pulling the historical data.
Okay, and it's one of the users said it was nice that you're focusing on time windows around the growing season. Is that largely just to avoid clouds, or are there other signals that provides? They mentioned that they were using gap-filled Landsat images to look for the earliest month, and that improved their classification results.
Yeah, so I love the compositing feature of Earth Engine, and I think it's one of the greatest things about it. So and that's what I'm doing as well. Ideally we'd have a daily composite, right, but we don't have that. So with Landsat and Sentinel, you're trying to create these time windows, and at times you do have to fill them where you just have no data. It was just cloudy all the time, and it's a challenge. But within that thing I demonstrated, I do have to take that into account at times and gap fill effectively with an average data set.
Okay, and one final question. What do you think the potential impact is for a near real-time CDL, as you've kind of envisioned? What's the impact to farmers, then what's the impact to USDA?
I mean, so my goal, or our goal within USDA, is usually statistics, so trying to generate how much planted area, which helps inform the food supply ultimately. So there's just trying to understand the planted area, but there's also the question of how much that area is growing in terms of yield. So a real potential powerful thing is if you can really nail down where those corn and soybean fields are, then you can really track just those pixels through the growing season. And right now we have to use sort of generalized masks to understand, well, this is kind of a corn area or soybean field. But if we can get those classifications really early in the season, and then we can start integrating deeper time series data like MODIS to really look at the condition and progress and yield ultimately. And I would like to think it's exportable internationally as well. So if we can get an idea what a cornfield looks like in the U.S. over the large geography the U.S. has, maybe we can apply that to Argentina or China or Europe, Australia, you name it. So that's the next frontier, I would say.
Great, Victoria. One question came in. How do you actually link the remote sensing data with the in situ measurements for water quality?
Currently, we are using an R script.
Okay. Maybe any elaboration on that? I think they were kind of interested in like what the actual sensor is providing and what you're actually correlating it to in the remote sensing side.
Yes. So we take our chlorophyll concentrations and compare them, doing a bilinear regression statistics to look for performance metrics that is compared to Sentinel-2 and Landsat 8. And that is how we develop our that is our selection criteria. And then from there, we implement in Google Earth Engine.
Okay, thanks. So how far off are you from a near real-time HAB dashboard for Idaho?
For Idaho, I don't know. I would reach out to the Idaho folks to ask that question specifically. But for Texas, our timeline is hopefully over the next year if we can achieve success.
Okay, and you think that that'll scale nationally as well?
These are awesome questions because ultimately this is a water mission area, a USGS water mission area collaboration. And I think the ultimate goal is to be able to apply these methods across geographies. And our Texas study site is currently what we're working on, but hopefully the methods can be scaled up.
Great. Josh, another awesome talk. And it's really great that, GEVIS continues to be shared so openly to benefit others. Can you talk a little bit more? There was some general interest that came up in the comments about the gridding approach and the concept of interim assets. It seems like that would be applicable to Dave as he, wants to scale up as well. So anything that you could add on that?
Sorry, say that again.
The gridding
asset
approach and the interim
and,
assets and the performances that you've achieved through that.
Yeah, so in terms of the Earth Engine assets, the cloud scores and TDOM statistics, that's something that internally, specifically Ian Hausman with our group has worked on developing. He's going to, I won't say he's going to. There's supposed to be a methods paper on those. And then in terms of integrating those cloud scores into assets, we take the entire Landsat time series all the way through Sentinel imagery, and we use these different normalizing functions with the cloud score. And then in terms of the temporal dark outlier mask, which masks out clouds and shadows, we calculate those statistics for the entire CONUS for different tiles, and then we store those in Earth Engine. The reason why we do that for the whole time series is because that can be increase your computation time if you're doing that on the fly, opposed to just storing it in assets and then pulling it in and using it to mask out your artifacts and your imagery. The big hurdle for that is, if you're just an individual researcher or somebody getting the credentials the space in Earth assets to do that. So, and then I think that answered the second part of the question. Was there a first part there?
No, that was just a little bit more. Yeah, I think there's just some interest in the methods. One of the speakers who's coming up, Joaquin, in the next block, was asking how big are those tiles, for each data set, and then you're not downloading these, right? I mean, you're using them as an interim asset for the next process in Earth Engine.
Yeah, everything is stored in Earth Engine as assets. So the metoid composites are ran for annually from 84 through 2020 now, and we can update those. We have scripts to update those as we go along and get more imagery, or as more sensors are launched. And so, yeah, all that's stored in Earth Engine, so we can just quickly use that data. And then each tile is like 250,000 kilometers squared, give or take. So pretty large areas, about the size of the state of Colorado. So for reference, and so yeah, that's just kind of some general background. But I'm happy to talk more with anybody. Feel free to reach out through my email. And I would say the GViz package or module, the GViz is something. There's modules within GViz that you can use that have the cloud score functionality and all that built in with them. So yeah, feel free to ask me questions or reach out.
Great, thanks, Josh. Shusheng, awesome talk. Just have a quick poll here. Who in this panel is familiar with Gmap? Has anybody played with it before?
No, but I think I will now.
Yeah.
Because we convert all our scripts from JavaScript to Python, which is good to do, to keep your Python skills. But if there's a way to automate that, then.
Yeah, and it looked like Liza had as well.
Yeah, you can just copy and paste. If you have a bunch of script, you can also just use the module to automate all the. If you have a lot of scripts on your computer, if you just want a snippet, you can just copy and paste and then to convert automatically. But the caveat is that it only works for those like computational script. If you have like GUI, like interactive GUI in your JavaScript, that's not going to work because it's more complicated.
That makes sense. Yeah, I think you do an amazing job. By the way, he's an amazing Twitter follow because he's seems to never stop working and puts out amazing resources all the time. Just in this last week, I mean, you put out the resources, the videos for using cogs and the notebooks for it. And that's a really complete approach too, right? When you're sharing this, you're putting together a Jupyter notebook with an example, you're putting together a YouTube video. And so I really appreciate that. Any insights on like how are students at University of Tennessee leveraging Gmap in the curriculum or Earth Engine in general in the curriculum?
So not right now. I actually taught a course called Spatial Data Management in the spring last year. And so initially I was teaching them using JavaScript, but also I prefer using Python. And at that time, it was not very like intuitive to do interactive mapping with Earth Engine. And that's why I developed a package initially called GE Hydro. But then I kind of redesigned it and then created a package called Gmap. And then I released to GitHub. People like it. And then I continued to add features to it. So it was big built upon the materials I teach in class. But right now, it's more like the general Earth Engine community.
Okay, great. And one final question. Can all the functionalities be used in R through Reticulate?
I have not tried it before. So because the package is built on top of IPyLiblet. If IPyLiblet works in, let me say it now, probably interactive stuff might not work, but for those that's only like in command line mode, you should be able to do that. So for example, exporting data like in the batch mode or some other things just doing computation. It should work in R as well. There's also an RGE package, so you can also check out the other R package specifically for GE. Perfect.
All right. Well, unfortunately, that wraps up our time. We are now 3 rounds through this talk, and so we're going to take a quick 5-minute break. Right, let everyone grab a drink, quick bio break. Please stick around. We'll be back with our 2 final rounds in about 5 minutes. Thank you all.
Thank you. Take care.
All right. Thank you, everyone, for hanging on there through the break. Anybody that's most recently joined, just a reintroduction. My name is Sean Waltman. I'm Google's cloud geographer, and we are about a little bit over halfway through the first ever virtual public sector meetup for the Geo for Good conference. So we've had 3 amazing rounds of lightning talks so far, and we have 2 more extraordinary talks rounds to go. And so thank you. And panelists, prepare for coming up after this next section. We're going to kick off round 4 right now.
From Mexico and the Instituto Politécnico Nacional, Joaquin Salas.
What I'm showing you here is a map for a portion of Mexico City. In red, I'm coloring the vulnerable settlements, and in yellow, the neighborhoods that are better well off. We're able to plot this information at the resolution of residential blocks. One problem that we have is that we have constructed this graph with data from the 2010 population census. So the questions that we have are, can we obtain this map out of satellite images instead of house-to-house surveys? Can we do it nationwide? In 2003, the UN Habitat made a suggestion about how to describe vulnerability using the following criteria: whether a house has running water, whether a house has sewage, the number of occupants per bedroom, whether the house has floor made of concrete, and whether the house has access to a toilet. Fortunately, one of our partners in this project, the National Institute of Statistics and Geography, generates this information out of census data. Here, we illustrated the residential blocks in Mexico as a country and an expanded illustration for a portion of Mexico City. Each residential block has a GPS location and an average number for each of the indicators for a mention. Out of each location, we obtained a Landsat image in RGB corresponding to an area of 600 meters times 600 meters. There are several proposals to summarize the predictors available into a slum severity index, including principal component analysis. However, after the analysis, we came out with the idea of projecting the measurements to a unitary vector in a 5-dimensional cube, traveling from non-vulnerability to complete vulnerability. Our index is just the dot product between this reference and the corresponding descriptor. Deep learning has become the technology of reference in many computer vision-related tasks. Thus, we investigated how to establish a mapping between the satellite images and our vulnerability descriptor. We compared classical techniques such as ResNet, VGG, but a simple architecture called LeNet gave us the best performance. Using our descriptor, we are able to map the 2010 survey census data to satellite images at residential block level. Here, I'm showing you illustrations for the results at nationwide level and at local level within a city in one of the states in Mexico. We obtain this information at residential block level. At this moment, we're waiting for the 2020 census results to confirm our findings and assess whether our method can be applied to intercensus data to acquire up-to-date information about the sprawl of vulnerable communities. More now that face-to-face interviews are in jeopardy. Interestingly, a simple convolutional neural network architecture outperforms more complex ones. We will look into this. We are planning to start studying other types of images, including SAR and multispectral, which offer some advantages, including better spatiotemporal resolution. Thank you very much for your attention to this talk.
from the United States of America and the National Geospatial Intelligence Agency, Matthew Hume.
Hello, my name is Matthew Hume. I'm here to talk about Waldo. I'm an image scientist at the National Geospatial Intelligence Agency. Not joining me, but a participant in this project is Dr. Jason Roberts from the Australian Geospatial Intelligence Organization. Let's go ahead and get started. So we're here to talk about a script we made called Waldo. I'll get around to what that stands for in a moment. Waldo was a script designed to help look for construction activity. So we ended up gravitating towards the annual greenest pixel composite, which unfortunately is no longer updated due to a change from Google, but it was a really fun source. What we do is we use that script, we add a time band, and then from that time band, we look for a period where there is a low Ndvi. As you know, Ndvi is a measure of healthy vegetation. So that low period frequently is associated with construction activity. So we tinkered around with this idea for a little while, and our first script was something like this. So this is, I believe, a place in China. And here's what it looks like when you look at the low period. You just see that there's some outlines around some buildings and kind of muddled mess everywhere else. And this was the step in the right direction. Shows areas of change, but it's too cluttered. And then with some tinkering, we came up with Waldo. So Waldo was the next version. What we did was, instead of just looking at the low period, we looked for a drop from one year to next. And then we basically flagged the areas that had a significant drop and then only visualized those areas. And we visualized them by the year of that drop. So it's a raster of change, only where change significant enough to have been flagged shows up. So here's what kind of the script looks like after Waldo is done with it. And you can see how areas, certain housing blocks in this image are flagged. The different colors are associated with different years. And we switched to a different color palette soon after this. And Waldo stands for Worldwide Activity Locator through the Disruption of Organics. It's kind of a mouthful. But since we were looking for stuff in Waldo in the United States, I think it came from somewhere else, but it was a popular book series for kids. So Waldo, what can it find? Here's an image of, I believe, Moscow, and you can see all the little colored specks around the, from basically the southwest to the southeast. Those are all roads, areas of development, just areas where Ndvi was dropped at some point. And then the greener areas are older periods and the redder areas are newer periods. And I believe this is from around 2003 to 2015. So to give you an idea of when this occurred. Go to the next slide. Here's another way we utilize Waldo. We found an aqueduct that was constructed in China up near Tianjin. Just another thing we thought was interesting. These are just a few examples, but we actually ended up using this to kind of get a rough measurement of area of developed land for a given location. And Waldo worked on a few other things. Here's another example real quick. This is a tailings dam failed in Brazil in 2015 and flooded the river. You can see the change in the shoreline when Waldo picked up the drop in Ndvi from the vegetation getting killed from all the pollution. So just another example of how we used it, but that's my short talk on Waldo. I guess I'll be ready to take any questions if anyone has any. And that concludes my talk. Thank you.
From the United States of America and the U.S. Forest Service, Claire Simpson.
Hi, my name is Claire Simpson, and I work at the Geospatial Technology and Application Center in Salt Lake City, and I'll be presenting this project that we've titled Parsing the Landsat Time Series to Unveil Pre-Disturbance Landscapes. So the goal of our project is really to peel back disturbance and get at this sort of stable base state environmental conditions. And the way that we're doing this is using Landsat, which is an algorithm I'll talk about next, and the Landsat archive to remove images from the time series that are affected by disturbance and ultimately produce these disturbance-free composites. So what is Landsat? So Landsat is a spectral temporal segmentation algorithm. So what that really means is it is looking to parse down a dense spectral time series of data, so Landsat imagery, and reduce this into individual linear trend segments. So it's trying to reduce noise and just capture the general spectral linear trends. And it's important to note that it operates on a pixel-wise basis. So each of these time series are individual pixels, and that's what this figure on the right is trying to show. We're just going through an imagery stack at the level of a single pixel and then turning that into this spectral time series data. So what Landsat does is it takes this dense pixel time series trend and converts that into individual segments. So here at the top, we've got just these pixel by pixel values, and in the middle, you can see that Landsat is converting this into individual segments. So we've got this first segment that is essentially representing a period of stability, and then you've gotten a decline, which most likely represents some sort of disturbance event. And after that disturbance, you've got this long period of recovery. And we're measuring this in the level of one single spectral index. So here we're looking at the normalized burn ratio. And then in the bottom here, you can just see what sorts of valuable information that we can get from these Landsat segments. So you got the bounding dates of these segments, as well as the magnitude and duration of the segments, which can give us some sort of information about what kind of segment they're representing. So whether that is a disturbance or recovery or a period of stability. And for our use case, we are really looking to create sort of stable layers for modeling. So for some modeling efforts, so for example, modeling soil properties, it's really useful to have disturbance-free information and reduce the amount of noise and confusion that you are introducing into your model. So at the bottom here, we have some Landsat images that's just representing what it might look like after the disturbance. And that's really what we're trying to remove. So how we're doing this is we are using Landsat within Google Earth Engine to parse the Landsat archive and come up with disturbance-free imagery composites. And this application of Landsat is pretty non-traditional. So often people that use Landsat are looking to highlight disturbance, but we're actually looking to remove it. And Landsat is super valuable to us because it really operates on in an automated way. And when we have such a large study area, so for us, we're looking at the entire lower 48 states, it's important that we are able to automatically detect and remove disturbance. So now I'll go over a real-world example of what Landsat might be doing behind the scenes. So here we're going to take a look at an area of the Rim Fire, which burned in California in 2013. And here in this plot, we're looking at the single pixels linear time series. And at the bottom, we have some Landsat imagery that is just representing some images from both before, during, and after the fire. So here we have a period of stability. So in 2010, we have the stable pre-fire period. In 2013, that's when the fire actually occurred. This imagery is taken before the fire, so you don't see the effects yet. And then in 2014, you can really see the strong effects of this burn scar. And in the graph, likewise, you can see this strong decline in the normalized burn ratio that's representing that disturbance. So for our disturbance removal process, we are just looking at that period of stability. So here we have the 2010 and 2013 imagery, so we don't see any sort of evidence of burn. And we're just taking all that imagery from this whole time series based on this segment. So with Landsat, again, we can get that start and end year of certain segments, and then just take imagery that falls within that. And the result of this is just a disturbance removed composite. So because we are removing all the evidence of the burn, we're just taking this pre-disturbance imagery and we can get a more stable more stable image. So you can see this is that same image that's taken around the rimfire, and you don't see any burn images. And I'll just mention also the way that we're detecting this pre-disturbance segment is it's a rule set. So there are infinite ways that you could be parsing this time series, but we're essentially looking for the earliest and most stable and longest segment that we can. And then I'll close by mentioning a few limitations to this approach. So obviously you can have multiple disturbances in an area, and that can make it very challenging to access any sort of stable segment or base state conditions. And then again, Landrender operates pixel-wise, so the outputs can be a little bit noisy. And then finally, obviously we are unable to see any imagery that occurred before 1984, so before the Landsat archive, and therefore disturbances before this time period are not accounted for. So thank you very much. And I'll just lastly mention that funding for this work was provided by GTAC. So thank you very much for watching.
From Canada and the Alberta Biodiversity Monitoring Institute, Jen Hurd.
Hi, everyone. My name is Jen Hurd, and I'm a remote sensing scientist at the Alberta Biodiversity Monitoring Institute. Today, I want to talk to you about some recent work that we've been doing looking at forest harvest areas and regeneration in those areas across the province of Alberta, Canada. Now, so what I want to describe to you today is how we've been using Google Earth Engine to develop tools and data sets to support land and resource management within Alberta. And this is something that we haven't been able to do without Google Earth Engine before. Now, Alberta is a very large place. It covers over 600,000 square kilometers in Western Canada, and a lot of that is forested. So forest harvest, or the removal of these trees for timber and forest and paper products, is an important industry in Alberta. And in fact, Alberta is actually a world leader in forest management and sustainable forest management practices. So that means that these harvested areas are then actively monitored and supported in their regrowth. And that regrowth of the forest is what I'm talking about when I'm talking about forest regeneration. So at the local scale, because this is actively managed, this is very well understood. But broad scale, on a regional or provincial level, patterns of regeneration aren't that well understood yet. So what we've done is we've leveraged Google's Earth Engine platform in order to get that broad scale perspective. So what did we do? We took existing harvest area polygons and we brought them into Google Earth Engine. And within there, we analyzed the Landsat archive, over 30 years of satellite imagery. We used a tool called Landtrender in order to extract trends from those time series. And from that, we generated a number of metrics related to regeneration, and we summarized those over the harvest area. Now, when I'm talking about regeneration here, I'm talking about changes in the spectral signals. So those spectral signals will decrease as vegetation is removed, and then they will increase again as vegetation is regrowing and regenerated. So I'm talking about spectrally based regeneration here. So what did we find? We found that in our final data set, we had over 66,000 harvest area polygons with spectral regeneration information. Our Landsat time series covered 33 years from 1984 to 2017. And our harvest areas ranged in size from less than 4 hectares up to over 500. Now, after 5 years, harvest areas were on average almost 60% spectrally regenerated. It took an average of 8.8 years for harvest areas in Alberta to reach 80% spectrally regenerated. And 63% of our harvest areas had reached their full pre-harvest signals. Now, this is really cool stuff. It's really interesting, and no one's really looked at regeneration in this broad pattern in Alberta before. But as I said, we're looking at spectral regeneration, and this is different from what's measured on the ground when you're looking at regeneration. What we're measuring, our metrics don't directly measure things like species composition or vegetation cover, ecological function. So our next big step is understanding that relationship between our broad complementary spectral regeneration metrics with what is seen on the ground. And we're actively doing this right now. We're collaborating with industry and government partners in order to understand that relationship. And then on top of that, build some meaningful applications. Now, when I'm talking about meaningful applications in Alberta, especially, cumulative effects management is an important area. Alberta has a lot of human activities going on its landscape, including natural resource extraction. And so understanding and managing the cumulative effects of all of those activities on our landscape is really important. So with our data set, what we'd like to do is help to answer questions like, which harvest areas are underperforming and need a little help, or which harvest areas, on the other hand, are on a trajectory towards full regeneration and regrowth. And can spectrally regenerated harvest areas maybe be removed from a human footprint map? So to wrap up, with the help of Google Earth Engine, the Landsat Archive, and the Landtrender tool, we were able to generate patterns of spectral regeneration on these harvest areas across all of Alberta at that provincial and regional scale. Now, that's all I have time for today, but I want to say thank you for listening in, and I really hope you enjoyed it.
From the United States of America and Planet, Sam Roy.
Welcome to Planet Data Integration and using Google Earth Engine. Now, in the past, a lot of you has asked us, or a lot of you have asked Planet as a data provider questions about when exactly is Planet data or commercial data going to be made available in Google Earth Engine. And we want to focus on that question itself, but we also want to give you the tools to do this yourself. So with that in mind, this talk is designed to talk about that integration. Now, in the recent few days, we have launched a program under which you will have the capability that if you have a Planet account and if you have access to data, you will be able to deliver your data not just to existing cloud accounts, but you will also be able to deliver the data to a Google Earth Engine collection, similar to how you have delivered it in the past. Now, there is a caveat here that you need to have a cloud-enabled account, and there are guidelines and instructions for doing all of this at the end of these slides. So hang tight till I reach towards the end of the slide. The slide right now is actually showing you how to make a simple Postman request and to go in and see where these data sets are and how these data sets are going to be delivered into your Google Earth Engine account. So for example here, I've created a collection called G4G20, and this is where all of those images are going to be delivered. Talking about data, I wanted you to start with data that doesn't cost you anything. So I wanted to talk a little bit about the Planet Disaster Data Program. I don't know if a lot of you know this, but we have a disaster program that is designed to help natural or man-made disaster data made available to first responders, to humanitarian organizations, and to other users who want to utilize the data and to come up with solutions or to come up with their own methods to help. And this data is provided under an international charter, and this is under a CC BY licensing. And you can find more details on this program under this website that I have listed on the slide. So I would recommend that you apply for this data set, and you can get alerted every time there is disaster data that's made available. Again, it's free of cost, so you can test out Planet data delivery into Earth Engine using that link. Going into the next slide, what I did was I took Amphan, which happened in Bangladesh, which was Cyclone Amphan. And what I did was I ingested these data sets into Google Earth Engine, and I want to show you how it behaves. Now, a lot of you already know what I'm doing. You already know that we can do the filtering, we can do metadata assessment, we can do size queries and things like that. But I wanted to give you an example that when these images are ingested into your Earth Engine collection, all and every metadata in your Planet data sets are also available in your Earth Engine data sets. So it's not just what I'm showing you. It's not just the visible data set that's available to you, but it's also the associated metadata that's also available to you. Thinking back again, you can build apps on the fly. So for example, this is I think it's a 7-day or a 14-day composite creator. What we're trying to do is we're creating these composites on the fly over that same area of interest. The other thing you will see is the type of base map that I'm using is called Lost in the Desert. This is another completely separate discussion on, hey, Earth Engine allows you to add any single base map that you wanted to. You can make it look and appear the way you wanted it to be, or highlight the points or focuses that you want to. And going to the next one, again, talking about applications. I don't have to tell you, all of you are experts, are coming from different backgrounds and have local knowledge on where you want to focus, what are the features you want to look at. For example, here I'm focusing on water detection and trying to see if there is flooding going on in a specific area within this data set. But you should be able to do this on your own as well. And this is exactly the point of this. The first path of solving this problem is making the data available to you. The second path is then connecting the data and making it truly accessible. This is the first time where you're no longer constrained by bandwidth, by thinking that, oh, I don't have the storage space to store gigabytes and gigabytes of Planet data. If an image is delivered directly to your collection, you as a user are able to use this even in situations where there's low bandwidth. This truly makes data accessible. It's not just available. There's a difference, and that's what I want to focus on, that it truly makes data accessible within Google Earth Engine. With that in mind, I want you to keep these resources at hand. There is all of these documentation for Planet Earth Engine integration, including how to get your own Cloud Alpha account at the developers.planet.com, the Earth Engine integrations page. And if you have any questions, you can find me. I should be available within the meeting, or you can email me at sam.roy@planet.com. I will make the slides available as a part of the presentation. And again, thank you for coming.
Awesome. Awesome. Thank you all. And Sam, I like that, the difference between accessible and available. I think that's pretty succinct. So please, all of my panelists, please come up here. Joaquin, let's go.
Hey.
Jen, good to see you. Sam, Matt, Claire, wonderful to see you all today. Thank you.
Thanks to you.
As I've been doing with limited success for all of these, I wanted to first give you all the opportunity, if you saw anything in each other's talks that you had any questions about, before I go to the questions that we have from the audience.
I do have a question. Oh, go ahead. Yeah.
Jen, we'll start with you.
Sure. I had a question for Claire. I really enjoyed your presentation, Claire, and I loved how you explained Landtrender so well. That supported my presentation very well, so thank you. So my question was around, so I love what you're doing. That's really neat stuff. How do you deal with areas? So for example, if you have a grassy area and you have gradual, say, tree encroachment happening, or something that's sort of a subtle natural change in the landscape, how do you deal with that in your compositing?
Yeah, so I guess I would say we don't really deal with it. Anything that's a gradual change over time, Landtrender probably wouldn't pick up. Well, with our rule set, we're looking for strong disturbances. But I guess we're not so much trying to remove those subtle changes in the landscape. We're just looking to remove the strong differences that would influence noise. But having said that, I would say that type of change would probably register as some sort of slope, and we're looking for the Landtrender segment with the most stable segment. So hopefully we would be choosing a Landsat pixel that's not changing as much, or sorry, a segment.
Thank you. Yeah, it would be tricky.
Yeah.
Go ahead, Joaquin.
Yeah, thank you. Thank you very much for your nice talks. I guess that my question was in the same direction. I was wondering how do you deal with the gradual change due to change of seasons? And I think that this question is addressed to several of you.
Sorry, I kind of cut out.
Sorry,
was that directed at me?
Well, I think that the three of you, Jan, Matthew, and Claire, talk about the changes. But I was wondering how you deal with seasonal changes.
Yeah, so for Landtrender, it's you're looking at annual composites. So supposedly that would mitigate any specific seasonal variations.
That would be the same for us when we're looking at imagery mostly over the summer, maybe a little early spring and later summer. But yeah, it would be the same approach for what we're doing.
Same for us too.
Okay, great. Wow, this is awesome. This is exactly what I wanted to see, right? Like, 4 practitioners having this type of conversation. So I'm glad you all were able to meet. We do have a lot more questions actually on this one. So for Joaquin, do you have any indications as to why LANET was so much better than the more complex networks for your?
So right now we're looking into that. Measuring vulnerability is a very tricky question, and also collecting and constructing these indexes of vulnerability is an issue. So right now we are investigating into that, trying to assess also how well all algorithms perform with respect to ground truth. So it's not just how well they perform with respect to an index that we constructed, but how well they perform with respect to what we actually see as vulnerability on the ground. So we're looking into that right now.
Okay, great. And then was there anything that you're expecting to gain from additional sensors, SAR? Was it just higher temporal resolution, or was there anything else that you were hoping?
So right now, what we are expecting to obtain out of satellite images is the possibility of generating this information as we need it. Because right now, the information that decision makers have is very outdated. So they don't know how to bring electricity, how to bring roads, or where these resources are more needed. So that's what we want to achieve with satellite image analysis.
Got it. Matt, super interesting. You said that the Geospatial product is no longer available. Can you remind me what the issue was there?
If I recall right, the data that was being used, because I'm pretty sure Google made the composites, but the data from USGS was discontinued. So I don't know if there's a plan to recreate that, but I think it was 2018 was when they ended that.
Okay, we'll look into it.
It's in the metadata. You can still find it in the data catalog, and it'll explain the exact reason.
Okay, and then so being that that's not available, has Waldo spurred any like further iterations around this idea for like kind of broad scale disturbance detection or change detection?
Yeah, we've, or mostly myself, have tried adapting it because the script doesn't really care what data set you feed it. Obviously, if you feed it something more seasonal, you're going to get a lot of seasonal change. We're at that point looking for annual change, and I've adapted it to work with Sentinel-1 data. But once again, you're catching image to image change with that. And I've played with doing it with some other things, but yeah, it's something I constantly looking for ways to try. But right now, there's so many different scripts you want to try out, and it's one of many. So this is something we actually made about 3 years ago. So we're still kind of see where it leads us.
Okay, great. All right, well, these are all. We should have had a land trender session clearly. So I don't know if Claire or Jen wants to take this one. But has anybody looked at expanding land trender beyond just a single pixel? Does it take in regions at all, or patches? The concept of patches at all, or is it looking at individual pixels?
I can jump in first if you want. In my understanding, it's not at this point. My understanding is it works on that pixel level. So we were wanting to look at patches, harvest area patches. So what we did was, after we had derived a series of metrics and analyzed on the pixel scale, then we used the reducers to look at per harvest area, sort of like zonal statistics. It would be neat to look at patches, but I haven't heard of any move in that direction on my end.
Yeah, I was going to say that exact same thing. I could see using some sort of zonal statistics approach on the front end. Like, I think the theory would apply well, but I've never heard of anyone actually doing that. Okay.
For Claire, can you just elaborate a little bit further on why? Because it's a kind of a different approach, right? A different application of land trender, where you're trying to remove the disturbance rather than detect it. So why is that important for detecting soil properties, et cetera?
Yeah, so with a lot of things that you might want to model, you don't necessarily want your input imagery to be contingent on the specific, I guess, quality at that time. So for something that's not changing very much, like a soil property that changes on a time scale that's much longer than the time scale of like a vegetation change, you really want to get the most stable inputs to that model that you can. So that was the impetus for our work.
Okay, and I just had one come in from Mike Toomey. How does land trender account for different band passes among the sensors?
I'm not sure how to answer that. I don't know if anyone else does.
All right, we'll save that for our upcoming land trender session, which we clearly need to have. Jen, question came in: are you differentiating harvesting from natural events like forest fire?
In a way, we are in that. That's why we bring in harvest area polygons that exist. The group that I work with, the Alberta Biodiversity Monitoring Institute, has this really great human footprint inventory that they update regularly, and it's a digital database of footprints, and so they've got harvest areas in there, and so we are using that to focus our attention on those harvest areas. That said, there are wildfires that happen on top of harvest areas and go through harvest areas. And so that's something that right now I'm looking at how I'm dealing with that occurrence. And right now because I want to look at the regeneration signals from harvest areas, I'm kind of avoiding areas where where wildfires are causing changes in the signal. But yeah, it's something that does happen on the landscape, and we're trying our best to deal with that in what we're doing.
Great. And then you mentioned like underperforming regions where regeneration's not occurring as quickly as you would expect. How does Alberta ultimately deal with that? Like, what is the law, and who's responsible for helping there?
I have to say I'm not in the forestry industry, and I'm not an expert on the subject, but my understanding, so in Alberta, forestry companies have a forest management agreement for the area that they're harvesting, and they're responsible for sustainable forest management in there, and making sure that regrowth and regeneration is happening, and that's also going to support them economically down the road too. And so they do a really fantastic job with their environmental work and ecological work in that area. And they do surveys periodically at certain ages after harvest, and they look at the area, and I'm not sure at what point they decide to do, say, maybe reseeding or other sorts of treatments. I can't really say, but I know that they monitor these areas, and if they're underperforming, I'm certain that there are things that they want to do in order to promote more growth in those areas.
It's a great point. It's both sides of it, right? It's the private sector incentive, but it's also the monitoring and enforcement piece for the public sector. One more for Joaquin, and then we have a bunch for Sam. You mentioned the 2020 census data coming. Is there anything in new that you're expecting to be able to be helpful there? Is it just going to be the recency of the data?
Right. So that will help us to verify that we're doing well and that we are able to track over time the sprawl of vulnerable communities. So we want it as a checking point, a verification point that our learning mechanisms work well.
Got it. Okay. All right. Last but not least, Sam, a number of questions here. I'll start out with, you guys had a pretty big conference last week, and you made some announcements around Google Earth Engine. So just to confirm, what you just showed is what was announced there in terms of having imagery delivered to your Earth Engine bucket. So
yeah, exactly. It was just I had to condense it to a 5-minute format.
Okay.
But essentially, yes.
First question is, when would you suggest that users do that versus just maybe leveraging a cog? Right? Is there certain products where that makes more sense? Is there a certain temporal aspect to it in terms of that approach?
So that's actually an interesting question, right? Because I was there at the meeting yesterday talking about cogs, and one of the things that they were talking about, the caveats of cogs, right? Like if you have hundreds and thousands of images, you might see some visible lag in terms of when you're processing, because you have to manage like the fact that the cog is being read by Google Earth Engine and then making it available, so there might be a lag. The other issue with cogs, it's not really an issue, is the fact that you would have to be pretty adept at making sure that the permissions are shared for the cloud storage bucket to the end user. So right now in Earth Engine, you could just go into an asset and say share, and you just type in the email address and that's done. Cloud storage asset permission sharing is slightly more complicated. So that becomes a challenge because you have to share at 2 levels. And that's where I would decide on, like, depending on who is going to use the data and how it's going to be made available. Now, I would say COG is beneficial from the point of view that right now everyone is limited to the 250 gigabyte standard storage. With COG or with cloud, you don't have that limitation. You can store terabytes of data in cloud storage and then access through COG. So, yeah.
Okay. Yep, that makes total sense. So we had a question here from Alexander. He said, will the planet data sets that are made available as part of the contract to combat deforestation, I guess, a Norway, Planet, KSAT, Airbus be available as assets?
That is still an active conversation, so I don't have any updates on that yet, but hope, look forward to some updates real soon. Yeah, on that.
Okay. And then from Corey, somewhat similar. If somebody brings that disaster data into a collection, can then they share that collection publicly? And is there any effort to kind of develop a public app that's using that Planet disaster data? But I think there's also a question there, like, is there just a general Planet disaster Earth Engine collection?
So there isn't really a general disaster collection. That's also a conversation we're having at the end of the week. But thanks for bringing that up. Actually, that gives me impetus to ask Matt this exact question. But that being said, if someone does bring in data sets into the collection, if you look at the disasters page, there are different kinds of licenses. So there's a CC BY licensing for share alike. So as long as you're doing a share alike, you can actually share the data with your friends, colleagues, make it available as an app. There is no restriction there. There is also CC BY NC licensing for if someone wants to use that to develop any commercial applications or doing R&D inside a commercial setting. So look at the license at the disaster space, but that should be pretty clear on like, hey, it doesn't restrict you from resharing the data or redistributing the data. Yeah.
Okay, and then one from Lucy from earlier. She's wondering if a time series data, will there be something to consider for someone who's thinking of analyzing time series using Planet data for a large area like Ohio for a couple of years?
If the data is made available to you, sure. If you have access to the data, like for example, apart from the disaster program, because I know that a lot of the users here are from the educational and research community, if you're at any public university, you already have access to 5,000 square kilometers of free Planet data every month. Anyone can apply for that who is at a degree granting university. But apart from that, if you do have access to a very large bucket of data set, you can ingest all of that into, I don't see any restrictions as far as, like, yeah, you can get state level data. The highest I've done is like half a state, but it can be done, yeah.
Okay, and I have one more question for Claire. How different are the results from Landtrender from those from GeoMedian, if you've evaluated that?
I have not evaluated that. And I have to say I'm not super familiar with the GeoMedian approach, but I would say our approach, we're explicitly removing disturbance. So if there's any sort of long process of recovery that would be impacted by a previous disturbance, we are explicitly removing that. So I think the main difference would come from that. So we're only looking at pre-disturbance imagery instead of just taking an average of the full time series.
Okay, great. Jen or Matt, any comments there?
I'm afraid I'm also not very familiar with the GeoMedian approach. So I'm afraid at this point I don't think I have an intelligent comment to make, unfortunately.
No problem, me neither. Okay, so one final thing, Sam, you did mention to me that you've got another meetup coming on. I think that might be of interest. So if you want to plug that real fast.
Yeah, we're actually doing a presentation on community, like teachers, and like there's a GEDU conference that's going to happen. And that's going to happen at 10 a.m. Pacific time. It's going to be about people who are teaching hackathons or people who are teaching classroom materials. Like if you're designing an entire course to teach for an entire semester, or you're doing a 2-day hackathon material, what is your method of teaching? We would love to learn that. We are also hoping to write a synthesis paper. So this will be the first time where a part of the, like whoever comes to the meeting can contribute to an actual paper that we hope to publish in a peer-reviewed journal on methods of teaching using Google Earth Engine and how that impacts the community. Yeah.
Okay, great. Well, thank you all. A really engaging conversation here. We're going to go to one final round of talks, and then we'll come back for Q&A and say goodbye to everyone. But stick around. We've got one more round of talks coming up right now.
Thank you.
From the United States of America, University of California at Berkeley, Benjamin Wander.
Okay, I'm going to spend today talking about remote sensing of genotypes and mortality risk, showing you an example of how we're using Google Earth Engine to think about land management. The challenge we're addressing is predicting how forest health will respond as climate continues to change. In particular, we're seeing a lot of drought-induced forest mortality throughout the Western United States. And when we try and make these predictions of future mortality, we tend to do it by making maps of the environment. And using changes in the environment to predict changes in forest structure. But of course, species in forests are not monolithic entities, but have a range of genotypes within them. So it would be useful as well to map out different genotypes within a landscape, and then use the interactions between the environmental change and the genotypic change to predict the mortality. Unfortunately, however, genotyping is quite expensive and involves a lot of DNA sequencing, meaning that it's not possible to do large multi-million pixel assays across an entire landscape. However, the idea we explore here is that remote sensing of genotypes within species should be possible due to chemistry variation in the canopies of different individuals. The use case that we're going to try and test that idea out in is quaking aspen. Aspen is a very dominant species throughout North America. You can see a range map in the bottom right there in green. And mortality has been going up by large amounts since the early 2000s. Interestingly, in this species, there are both triploid trees, which have 3 copies of each chromosome, and also diploid trees, which have 2 copies of each chromosome. It seems to be the case that the triploids are at higher mortality risk than the diploids based on some ground-based studies, but the question is, how does that influence the landscape scale patterns we see? So what we'll do in this talk is show you how we can map those out. The data we've been using for this are hyperspectral, so they cover a couple hundred different spectral channels at 1 meter spatial resolution, and they come from the NEON Airborne Observation Platform, which is a twin-engine aircraft with an advanced spectrometer, which was flown over southwestern Colorado for this study in 2018. And all of these very large data sets have all been organized and are now available in Google Earth Engine through the Department of Energy. Just to give you a quick look at what sort of data we're working with, on the left you can see a false color mosaic, and on the right you can see a zoom in showing an isolated forest stand within some meadow. So this is a data set large enough we really couldn't have handled it on a desktop, but Google Earth Engine has made it very possible. We can pair this data then with some DNA analyses from the ground, where we have an algorithm then trained to predict the ploidy level diploid or triploid of these trees based on their spectral properties. And here you can see for diploids in blue and triploids in red, there's quite a lot of spectral separability between these 2 cases. And in fact, if we try and do a classifier, we can get about a 90% accuracy, 10% error rate, splitting these up. What that then lets us do in Google Earth Engine is make these incredible spatial maps of the genotypes found within the species across the landscape. Here you can see a map of the diploids in blue and the triploids in red. And we know that these triploids are ones that tend to be associated with higher mortality rates. So it's pretty incredible to be able to see inside a homogeneous forest and through Earth Engine, zoom around and check out at 1 meter resolution what's going on with all of these trees. Interestingly, when we overlay this with some other aerial mortality surveys, we can actually show that the triploids in the system have more than twice the mortality rate of the diploids. So I think this is an example of the kind of insight you couldn't necessarily get without this high quality spectral data and without an informatics tool like Earth Engine. We'd be happy to share more about what we're doing. Please feel free to get in touch, and thanks for your attention.
From the United States of America and the U.S. Forest Service, Leah Campbell.
Hey everyone, today I'll be telling you a bit about the U.S. Forest Service's Landscape Change Monitoring System, or LCMS, and some applications that we've developed. LCMS is an ensemble-based change detection system that the U.S. Forest Service has been in development on for the last few years, and we're about to make it operational this January. And the system consists of pixel-based maps of vegetation loss, vegetation gain, land cover, and land use. And each of these maps are produced for each year from 1985 to the present. So you can imagine there's a wealth of information that we can gain about the history of areas within our country and national forests. This system is produced almost entirely using Google Earth Engine from start to finish. We create satellite image composites for each year. We apply change detection systems like Land Trender and CCDC. Then we put all of the outputs into an ensemble, feed it into a random forest model, and that produces these maps for each year. And again, all of this is done using Google Earth Engine. Then we've developed this website that we call the LCMS Data Explorer, where users can pan and zoom using the Google framework and learn a lot about the history of certain areas. So here's an example of a fire where I have zoomed in and clicked on one pixel. And from that, we can get time series of what has happened at that pixel throughout time. So these graphs show time on the x-axis and model confidence or probability on the y-axis. The pink line is the probability of loss throughout time, which you can see spiked in 2008, the year of the fire, and then went back down to near zero. Correspondingly, the gain probability increased for a few years afterwards, suggesting that vegetation was regrowing in that area after the fire. Then we can compare it to land cover. This graph is a little bit different because we're showing the modeled probability of each of these different land cover classes. But you can see that trees were the clear winner for every year until the fire. Then the probability of tree cover at that pixel dropped off, and barren tree mix was dominant, followed by trees and grass. And now trees are starting to resurge again. So you can imagine that Forest Service managers would find this to be really useful. And we've had a lot of requests for more applied tools and resources where they can really focus in on their needs for US Forest Service. So one of these examples is a burn area recovery tool that we created for the Bridger-Teton National Forest in Wyoming. We put this into an Earth Engine app, so it's a really user-friendly interface. And we're basically summarizing LCMS statistics over different polygons within fire boundaries so that these managers can evaluate how much an area is coming back from a fire. So here I've clicked on one of these polygons. And again, we can get a summary time series graph of loss and gain. And then in this graph as well, I've included the mean gain by similar polygon classes. So we can see that this polygon outperformed other similar polygons in the years after the fire. So then we can compare that in the second graph. This is basically just showing how it ranks compared to other polygons. So anything at 0 is average, and above 0 is above average. Below 0 means that it's performing below average in terms of recovery. And then again, we can compare that to the land cover time series like we showed before. In the map, the land managers can just look at a quick picture of which polygons are underperforming in pink or red, or doing well compared to other polygons in blue. So that's just a quick introduction to some of these applications. I invite you to check out these links. They're online. You can look at our pilot areas for LCMS and initial products. And if you're interested, keep in mind that all products are coming in January 2021 for the continental US and Southeast Alaska. Thanks so much.
From the United States of America and the Washington State University, Amanda Stahl.
This is part of a current research project that's a collaborative effort between my research group at Washington State University and the Palouse Conservation District in Eastern Washington. And we're looking at opportunities to streamline access to remotely sensed imagery with Google Earth Engine to increase ecosystem monitoring efficiency and effectiveness. We started by asking, how can Earth Engine contribute to ecosystem monitoring? And if we think about the cycle of adaptive management and policy evaluation, we know that monitoring plays a key role. Also, capturing and sharing learning and reconceptualizing the situation and objectives complete the cycle. In traditional remote sensing workflows, environmental data from imagery have been delivered in a one-way fashion in sort of a static sense to the end users who are engaged in environmental decision-making. We think that Earth Engine can increase the timeliness of data delivery and reduce that time lag between the data collection and delivery of information to decision makers. This can be done at a relatively low cost to complement existing ground-based monitoring strategies, and those ground-based strategies tend to be site-based, whereas Earth Engine can provide information at policy relevant scales to try to string together some of that site-based information and provide a larger context at which ecosystems respond to change. It also provides a platform for interaction, and this is not just between different users and developers, but also an opportunity for the end users to update scripts as new data become available and ask new questions as they arise. So really bringing the environmental data closer to the end user for decision making. We explored a case study in monitoring ecosystem condition in agricultural areas, specifically in Washington state. And you'll see here on the map, there are counties highlighted in orange. These counties are participating in a voluntary stewardship program. And the idea here is that the counties need to monitor and report to determine the effectiveness of voluntary actions in agricultural areas in maintaining or enhancing ecosystem condition. This needs to be reported at watershed scales. And so the task here for monitoring and reporting is to detect changes in natural vegetation condition and extent, protect the privacy of producers in doing so, provide robust analysis, but also a feasible workflow given budget limitations and capacity limitations. And so the pathway to implementation is a core part of this research. We focused on Whitman County, outlined here in white in the upper map in southeastern Washington. And here we're dealing with a primarily dryland agriculture system. In this area, ecosystem condition depends on moisture availability and management practices. So we need to try to distinguish interannual variability in moisture from changes that are due to changes in management or restoration actions. And so in Earth Engine, we automated a process to distinguish natural interannual variability at watershed scales, reducing the uncertainty in doing so. And you'll see in this map in the upper right that part of our approach was to extend the study area far beyond the boundaries of the county to include surrounding watersheds. And these bright white areas are active vegetation in naturally forested areas that help us account for interannual variability. At the end of the growing season, these areas are bright white, whereas the surrounding vegetation has primarily turned brown, and those areas are shown in gray here. Down at the bottom, you'll see outlined in yellow, these are the floodplain areas, which are ecosystems of concern that are addressed by this program. So we focused on those ecosystems in our initial study. Unpacking the pathway to implementation a bit, we began this process by partnering with conservation districts who are helping the counties to do their reporting. We discussed with them the potential applications of Earth Engine with imagery and worked iteratively with them to develop, evaluate, and revise the workflow. We also generated initial products to help in their next reporting cycle. And really our next step is to begin addressing some of the challenges and opportunities we've highlighted for integration into existing monitoring plans and protocols. This is covered in our current manuscript we're working on. So I'd like to acknowledge my co-authors on that manuscript, Alexander Vermeer and Laura Hines, and acknowledge our funding source, the BioAg Grant Program at the Center for Sustaining Agriculture and Natural Resources at Washington State University, and of course the Palouse Conservation District, without whom we could not do this research. And I look forward to discussing with anyone if they have any questions about more details of the analysis or other possible applications in other settings. Thank you.
From the United States of America, the University of California at Berkeley, Deepak Nagaraj and Alberto Todeschini.
Hello, and thank you for attending our lightning talk. Our project is about finding out how much of the world's land is irrigated for the purpose of farming. My name is Alberto, and I'm going to introduce the rest of the team. We're a team from UC Berkeley. Our students Deepak and Elle are in the data science focused MITS program, and I'm the course lead in artificial intelligence. We collaborated with Professor Paolo Dodorico, who's the chair of the Environmental Studies Department. We set out to do this project to answer two main questions. How much of the world's land is irrigated? And how have the extent and intensity changed over time? Our operating principle was that machine learning and model satellite data can help us answer these questions. You may be wondering why the focus on irrigation? That's because it is by far the largest consumer of fresh water. Global estimates put the figure at between 2/3 and 70%. We're using water with so much indiscretion that we're depleting aquifers and losing valuable cropland. This can ultimately mean food scarcity and change in ecosystems. This is just a very recent example from this very month that says that in the US, in the High Plains, we're already past peak grain production because of decades of unsustainable water withdrawals through irrigation. I'm going to hand it over now to Deepak, who will go into the details.
Thank you, Alberto. In the next few slides, I will first talk about our model and then how we use Google Earth Engine to develop it. We use three main datasets for our model. We use satellite, climate, and land datasets. All of these are available on Google Earth Engine as part of its data catalog. These are large datasets, sometimes in terabytes for a given year. Our model is a random forest classifier that tells whether a piece of land is not irrigated, low to medium irrigated, or highly irrigated. We developed and combined two separate models for croplands and non-croplands. As shown in the picture, location, albedo, and soil evaporation are important features for our model. Our model runs on all continents except Antarctica. Here's a part of our map that shows how our model performs. Greens represent good news, that is, the model agrees with the labels. Browns and pinks represent false positives and false negatives. We validated our model by visual inspection. We took 100 random satellite photo samples within false positives and false negatives. We could see that many of these did have croplands, so we think having mosaics of croplands and non-croplands confuses the model. In this slide, we finally answered the questions we raised earlier. How much of world's land is irrigated? 11%, 2005. How much has changed? It's gone up by 4% in the low to medium range in 15 years since 2000. And here's a picture of increased irrigation in Western United States that was picked up by the model. In the next few slides, I'll talk in a bit more detail about how we used Google Earth Engine. Google Earth Engine was useful throughout the project. We used it to explore data, train the model, make predictions, store results, and showcase results. At first, we developed our model within GEE only for United States. And during this exploratory phase, we found its API documentation, code editor, and data catalog very helpful. We use GEE not only for compute, but also for data storage. On the left here, we show the features table we created for model training. On the right, you can see some summary information for one of our data sets. Once we run our models, we also use GEE to plot graphs and create interactive maps. Here's the time series plot of irrigation on the left and a sliding pane app to compare irrigation on 2 different years. And here's the sample app we created to show irrigation. It has satellite data for 2005 also as a layer. If you reduce the opacity of irrigation layer and zoom in, you can validate the model results on any region you like. So that was a quick tour of our project. At this point, we'd really like to express our gratitude to the Google team for creating this platform. Earth Engine helped us through all the stages of model development and gave us confidence that we can do large-scale machine learning on geospatial data. We are continuing to develop the model. I'm happy to say it's also under review for publication as a research paper. Here are some details if you'd like to reach out to us or have a look at our source code. Thank you very much.
From the United States of America and Oregon State University, Jamin Vandenhoek.
Hi, everyone. My name is Jamin Vandenhoek. I'm an assistant professor of geography at Oregon State University. I'm here today to talk about some work that I've been working on with several graduate students at the Oregon State University Geography program around urban damage monitoring with time series analysis, all analyzed through Google Earth Engine. So just to provide a bit of context, conflict is, as we know, a global phenomenon. It's a very difficult problem to resolve. Civil wars are increasing in certain areas every year. The damage that can occur to cities is really a hallmark of modern urban warfare. Understanding how urban damage manifests across the landscape is really important for providing humanitarian aid, for getting civilians out, and basically for identifying just changes to the urban fabric, changes to infrastructure that are really important, not just during conflict, but also after the conflict. There's been limited applications of multi-temporal satellite remote sensing for monitoring urban conflict. It's, as you would imagine, very well suited for it because conflict is frequent but irregular. It's widespread geographically, but it's clustered and it's persistent. These are all phenomenon or characteristics of phenomenon that satellite remote sensing do very well at capturing. But we're not really there yet in terms of a sort of mainstream application. Just to walk through how this has played out within the context of Syria, we have a whole host of different data sets that tell us where conflict events have happened in Syria. If we zoom into northwest corner, we see a different distribution of conflict events. We can look at a different kind of understanding, territorial control. Well, there's a wholly different idea of the conflict distribution. Now let's zoom into Aleppo itself, a different idea of conflict. And then we can look at the United Nations, the UNOSAT damage map, which is derived from high-resolution satellite imagery. And we have yet another different idea of the geographic distribution of conflict events through the lens of a satellite by looking at urban damage. Now, this is really helpful, but it's quite limited in spatial scope and temporal scope. We just have really a handful of cities across the entire country of Syria that have been studied, and only during a 3 to 4 year period during the civil war, which started in 2011 and is ongoing. So there's a lot of you can imagine the millions of people that are around Syria, the hundreds, if not thousands of cities that have experienced damage. And we have such a narrow viewpoint. These all have different benefits. They move from daily to annual, some are at settlement, some are at infrastructure, but satellite imagery, as we know, can span all of these domains. And that's what we tried to seek in this study. So we gathered surface reflectance corrected Landsat data over Aleppo, Syria from 2000 to 2019. It's about 600 images. We did standard pre-processing, removed clouds, removed shadows. We harmonized between the sensors, and we calculated a whole host of spectral and textural metrics that have been shown to be really effective in characterizing urban composition, including vegetative cover within urban areas. And then we ran a variety of time series harmonics and analyses on this data set to look at short, which is to say acute as well as long-term changes, and then we validated it. And I only have a few minutes left, so I won't be able to get into the entire scope of what we did, but I wanted to show a couple of sites where we see really promising results. So here's a site, you can see the yellow marker there. Sort of central Aleppo. If we zoom into this site, we can see that this was a building that has subsequently been razed, has been demolished, and we don't know exactly why, but presumably due to the conflict itself. And if we look at the time series signature of this site, I want to draw your attention here to the black line. We see this oscillation year in, year out, and it's similar to the sort of average harmonic before the war, which we have listed in orange, as well as the harmonic during the war, which we have here in purple. But there you can see some pretty prominent deviations. Those deviations that we've measured through, this is our composite damage index, are right in line. Two of these in this green column are right in line with a date that we know had extensive damage on the ground through our validation data sets. We pivot to another location here, this blue marker. Now this is a partial damage site. Similar kind of layout. We know as well, the green window here where we have extreme damage. And then we look at our product and we see these plots. I should have changed the y-axis here, but these go off the charts. Our index really detects prominent change during these time. And so what we're seeing is this, not only can we validate during that time, we're also seeing after, in this case, other extreme changes. What about this hospital that has been repeatedly damaged? Here it's in eastern Aleppo. If we zoom in, now this is the Google Earth Engine snapshot itself. We see same sort of peak after peak after peak of sharp damage states. if we think about this in composite, we can start generating ideas of cumulative change across the entire time span. And this is a wholly new idea of understanding how urban conflict is manifest across the landscape. Thanks very much for tuning in to this very short but still over time presentation. I'm here today and happy to answer any questions you have. Thanks so much.
Sorry, I realized I was on mute. I was saying thank you and give it up for our last round of speakers. So please come on up and let's have our panel. Hey, Benjamin, Deepak, Leah, Amanda, Jamin, how are you?
Hi, good.
Good. Well, thank you for all for not only pre-recording your talks but also being here today. I wanted to, like everybody else, did anything jump out to any of you? Any questions that you have for the colleagues here before we go to the questions that we have from the audience?
I had a question for Jamin. I thought your talk was really interesting. It's so different than what a lot of us are doing, but there are so many similarities within the remote sensing framework. And I was wondering if when you're looking at that harmonic time series, if you're going through each of them individually and interpreting it yourself, or if you're feeding it into some kind of algorithm to detect changes. Like what it reminded me of the CCDC algorithm, which is on Earth Engine.
Mm-hmm. Yeah, all the harmonics are calculated at the pixel level. As I mentioned, we have a pre-war and a mid-war harmonic, which themselves differ in pretty interesting ways. Yeah, everything's automated through Earth Engine, so we basically have a whole series of intermediate other time series, intermediate time series signatures that I didn't show that get us to that composite damage index, and all of that's automated, and we're at the stage now where we need to dig into what the kind of develop a different series of thresholds for magnitudes for sensitivity of that index. So obviously the higher our threshold, the less damage we're going to see, and that's probably a good thing to do. We don't want to be claiming that there's extensive damage where we don't have any grounding to say so. But the approach we've done is meant to be self-correcting, it's self-calibrating, it's place-based, it works over time. So it's meant to be, it's fully automated, and now we're at the stage of trying to figure out to actually do that rigorous interpretation to know what the automated results are telling us.
Yeah, that's great. Actually, I'll follow on because we had some questions come up in terms of, can you really differentiate the severity of damage, total demolition versus, holes in the roof or side of the building, for instance. So like what extent you can detect?
That's a good question. This is the concept here is called the threshold of detectability. Yeah, we won't be able to detect a damaged roof unless that roof is, 30 meters by 30 meters, basically, or has such prominent contrast such that it's a white roof and in the middle of it there's a huge black hole. Maybe we could see that, but it's quite difficult with the Landsat level resolution to detect those small scale changes. That said, at the sites we've looked at, partial damage, complete damage, repeat damage, all of those are coming through in different areas. And the real value, I think, is not just a single event. That's the whole motivation of the work, actually, is not to think about conflict as a single event, a single bomb exploding, but rather there's a conflict chronology. And the last hospital, the last slide I showed was a hospital that's been struck up to 17 times through on-the-ground reports, and in our approach, we're seeing that over and over and over and over. You go next door to the next building, you don't see that. And it's the same composition, it's the same tile material, it's the same spectral conditions, but we see a totally different signature.
Yeah, I think one of the things that we talked about previously that stood out was the roads, right? And you had some insights in terms of why they stand out so much.
Yeah, the roads are really challenging because they're really dynamic. A basic assumption we have is that that the city doesn't change that much. So when we do see such an acute short-term change, that's what our model looks for. But roads, as we all know, right, there's traffic moving through roads, there are staging areas, there may be rubble on the roads, the road itself may be damaged, could be paved and then it's bare soil exposed. The bare soil could be saturated or unsaturated, all of those things could cause an effect. So as we talked about, Sean, as well, if you go to the north of the city, there's a quarrying area, and that quarrying area pops up as just like constant change, as you'd expect. It's changing every day. And the roads are sort of similar in that sense.
Yeah, thank you. Benjamin, really, really incredible work at granularity, very different end of the spectrum as well here, and amazing cost savings potential, as you mentioned. One of the internal comments that I had here was like, genotyping from remote sensing sounds bananas, but it's amazing to see what you've accomplished. I wanted to ask you about the NEON data that you used for that particular study, because I don't believe we have all of that data available. So is that something that workflow that you did to ingest it, or can you tell us a little bit more about that?
Yeah, I'd be happy to do that. The short version is that I personally didn't do it, but other people on our team took care of that, and I can paste a link into the chat describing that entire workflow. But suffice to say, it took several people's worth of effort to deal with all the airborne data and get it in and ingested, but everything is now public and available for use, so I'll paste a link in.
Okay, yeah, that'd be super helpful and super interesting. What do you think is happening biologically that the triploid aspen show up differently than the diploid aspen?
One of the cool things going on is that the different ploidy levels do have different physiology, we think. One of the big differences seems to be different investment in canopy water content and different investment in different carbon-based defense compounds, and those show up in the SWIR parts of the spectrum. So we're able to pick those different features out, and they seem to come out very clearly in the diploid-triploid differentiation. Another interesting feature as well is that the different water use we see may be due to physical effects of genome size change. So a triploid has 50% more nuclear DNA content than a diploid by virtue of just having extra chromosome copies, and that puts constraints on cell sizes, which then puts constraints on stomata, which then puts constraints on water use. So it's a lot of cool microscopic processes scaling up to the pixels that we're seeing from the air.
Yeah, that's amazing. So I'm probably, but like, can you expand on like how this could be used for other species as well? I mean, do you see a broad area study here?
I think the fact that we're working with aspen is useful in that it's a species that forms monodominant stands. So when we have a pixel, we're pretty sure that the only thing inside of it is aspen. And that means that if we were to scale this up to, say, Landsat or Sentinel-2, we could be pretty sure that most of the pixels would be spectrally pure. Obviously, for most forest types, that's not necessarily the case, except in maybe some high-latitude conifer forests or some tropical Marantaceae forests. And in those cases, I think we'd actually be in quite a lot of trouble in terms of unmixing all the different things in any given pixel. But I think as the spatial and the spectral resolution of sensors continues to increase, this sort of application could be possible in many other contexts in coming years. And certainly with drone-based hyperspectral sensors that give much higher spatial resolution, there's no reason this couldn't be replicated in other species.
Awesome, thank you. We did have another question come in from Alexander Hernandez. Is this NEON data available for aspen forests in Utah that you're aware of?
Unfortunately not. So this data was a custom NEON flight paid for by Department of Energy as part of a broader watershed project, and the link I pasted in the chat describes that. It cost about $250,000 to do the flying, your tax money at work, and unfortunately it hasn't been done in Utah. Okay,
I'm actually going to take this link and put it over onto the into the YouTube channel. But thank you for sharing that. Okay, for Leah, first of all, I just think the national scale of what you've done is really, really impressive, right? Just as at the outset, I wanted to ask for the burn area recovery tool. How is the data actually used in the field? I guess similar to the conversation we had with Jen in the previous round, like once they see that an area is underperforming, what's the life cycle of that information?
Yeah, so it's pretty experimental at this point. We're kind of working with them to figure out how they can use this data in the field. But basically we're using it as, or they're using it right now as kind of a pre-check. So in the spring, when they're deciding where they want to go out and do site visits, they have a pretty large area that they're monitoring, and not all of it is easily accessible by roads or things like that. So they can use a tool like this to look at certain areas that they think, okay, maybe this area needs some extra attention, but this area looks like it's bouncing back pretty quickly. So we're going to focus our initial site visits on the areas that seem to be struggling, and then actually get eyes on it and make sure that it's performing the same way they expected from the tool.
Okay, so that's an important function for cost optimization and also just prioritization of their job.
Yeah, exactly.
Great. Amanda, users were curious in terms of what other types of ecosystem monitoring you think would be possible. For instance, like invasive species tracking, things that don't really break down cleanly across county and state lines.
Well, I don't think most ecosystems break down neatly across county and state lines, right? So I think one of the really unique things about Earth Engine is that we can look at the county or state data, and then we can also pull the same type of data from a larger area and then look at that comparison over time. And so that's what we've done with automated land cover classifications in this study area. So I think there are many applications, and I think that honestly, the actual workflow that we used was very simple, and that was intentional. So I think, whenever we can distill out a relatively simple workflow and then apply it at different scales, it becomes really much easier to show and explain to folks that aren't used to dealing with that type of data. And I think that's where the benefit is. So, of course, if we're getting into invasive species or species distribution modeling or anything like that, it can become harder to deal with the uncertainty and caveats and conveying that to the folks that would be interpreting the data. But at the same time, I think the ability in Earth Engine to create a suite of different models and then move towards generating apps that we can train users in a little bit so they understand the queries they're putting in. I think there's a lot of potential there.
Yeah, that leads right into the next question. I thought it was great that you just kind of described working with the conservation districts and getting their feedback as an iterative process. What was most surprising or what challenged your assumptions the most through that process?
Oh, I think that, I'm coming from an academic background, and I think the needs, the priorities, the ways of communicating are all very different. And in the area we're working in, private property rights are very, very important. And that's something that becomes a very delicate situation to the point where none of this work could be used at all if the trust was violated at all of the landowners who are involved in the decision-making of what the monitoring strategies will be. And so there's a lot of relationship building that even though I anticipated there would be some relationship building, I really underestimated how important that is in this process, and just being incredibly respectful. And then, we are doing ground truthing, but everything must be anonymous. And so working very hard to preserve that.
And that's the privacy protection piece that you brought in.
Yeah, so by reporting only at the watershed scale and then keeping the ground truthing anonymous and confidential at the site scale.
Got it. That actually will tie nicely into my question for Deepak. So tremendously important work. I mean, the fact that you're doing irrigation monitoring at this global scale is amazing. I wanted to ask about, now that your model is pretty advanced, how are you approaching the data sharing piece of this with governments, and have you been approached for like drought monitoring violation type use cases?
Yeah, that's a good question. So we are mostly using our contacts within UC Berkeley, and we're talking to Environmental Studies Department within UC Berkeley for next steps here. We are also talking to the Water Management Authority within California for possible usages of our model, and to see if they can benefit from a higher resolution model just for California or even the western part of the United States. So those are some of the next steps we are taking. We are continuing to develop the model based on what we get as feedback.
Got it. All right. Well, that wraps up all the questions that I have from the chat room. Did anybody else want to have any final thoughts or any final questions? No? Oh, Jaman?
Just wanted to thank you, Sean, for organizing.
Thank you.
Great.
Yeah, no problem, Jamin. Thank you all. This was great, and we thank you for everyone that's been watching. We've had a lot of viewership on this, and I think it's been a wonderful session. Thanks to all the work that you all put into here. And the nice thing about this is you can share it. It's live, and I hope that at the end of this that we're able to get together in person, and then we're able to make the next Geo for Good event even more successful. And I hope that we fostered some connections between higher ed and the public sector. I know for me, it's been an absolutely wonderful experience. So thank you all. And I would finally ask for anybody that's presented materials, if you want me to update the YouTube channel with links, I'm happy to do that. If you just send it to me and say, hey, yeah, please put in this link to my paper or whatever it is, or my Earth Engine app, I will gladly do that. So that is going to wrap up the first ever public sector meetup at Geo for Good. I want to also thank our amazing production staff here at Google that has been running this and helping get everybody into the backstage. I couldn't have done this without you. And so on that, I will ask Pedro to play us out. Thank you, everyone.